Okay, and the attendees are coming through. We're up to 33.
Now?
I'm going to stop my video and...
Yes, same here.
This meeting is being...
We're getting some feedback. I hope that's... Does someone else want to talk a little bit and we'll see if there's feedback?
I can do a sound test. Mic test 1, 2.
Sounds great.
Okay. Good morning, everyone. Great.
So we're just waiting for all the attendees to come through the door, and there seems to be a bottleneck getting them through. But there's 147 right now on my screen. We'll be starting as soon as the attendees all arrive for day 2 of our workshop.
Yeah, and it may take a little bit because I sent out an email this morning to let everybody know we were starting at 8:30 because when we announced it yesterday, many of the people were already gone for the day.
Right.
Can we also promote Yi as a panelist, to a panelist?
Yeah, I don't see him logged on yet at all.
Oh, he just messaged in the chat.
Oh, okay, so, okay, good. Thank you. Okay, you are a panelist now, and I presume that Joanne, can you promote him to co-host? Thank you. Well, we seem to be stable at about 150 participants right now. Why would you like to start yet? You're muted.
I just discovered there's some other people who were in another website, another Zoom site. So I actually log on in both sites and get the people come into here. Okay, why don't you get started?
Yeah, okay.
Yeah, I was getting emails from people asking which one. So I've been sending out the 3491, this one.
Okay, yeah, we just had 10 more people come.
Great. We can wait maybe another minute or two and then get going. We're going to start with the Q&A this morning anyway. So for those who do log in around 9, they won't miss too much of the practical or other new topics that we're going to discuss today.
Okay, why don't people start dropping in questions? Good morning, good afternoon, good evening to everyone. Could you please raise question in the Q&A box that Ali can answer your questions?
Great. And I also have a few from yesterday that we weren't able to get to, so I will start off asking those. So first off, just to recap a little bit about the difference between the practical and the rest of the webinar. So we have some questions about whether or not those who are not part of the practical can also use the same data sets that those in the practical will be processing today.
That's a great question. Unfortunately, due to the time constraints, we ran a little bit over time yesterday. Today, we've had to opt to not start from scratch for a lot of the data sets that or at least a couple of the data sets that we are going to process that are publicly available on Empire. Some of the data sets we're processing are not on Empire, and so those we can't directly share right now either, but we're hoping that once this whole webinar is finished, we'll be able to make a bundle of the data that we used for the workshop and make that available to everyone to be doing what we're going to do from home. However, I should say that in today's session, I would say by far the more important thing is to be watching not really how to use the software, but all the explanations of parameter choices, the slides that I'm going to be going through, advanced topics. And so actually clicking the buttons may not add that much to the knowledge that you'll gain by simply following along and listening to what we're discussing, especially through the Q&A, which has been really great yesterday and today, hopefully.
Perfect. Okay, I'll move on to some questions that we had pending from yesterday. I'm going to start sort of chronologically from the chain of processing that we started on the T20S dataset. So specifically, I'll start with pre-processing first. When it comes to patch CTF estimation, can you elaborate more on how does patch-based CTF inform us about ice thickness?
Great, that's a great question. What I'm going to do in order to show you that is come back over to CryoSpark. And I will move to a data set that we're going to be processing a little bit later today and just show you exactly how the ice thickness measurement works. So what I'm going to do is create a manual curation job where I'm going to be curating exposures so that we can see the quality of the various exposures. That's going to make some diagnostic plots that will be helpful to explain this issue. But to begin with, what I'll show is some of the diagnostic plots that are created when you run patch-based CTF estimation. In patch-based CTF estimation, what you'll see is that we solve an initial defocus estimate, and then we refine that estimate. Here you can see that in this case, the data is tilted and the plane is kind of aligned with the camera here, so it's a straight line. What we're going to end up looking at is this last plot here. This plot is actually showing us the rotationally averaged power spectrum of the 2D Fourier transform of the image. And in order to explain what that means, I'll just jump back over here to the exposure curation job and show you an individual view of a particular micrograph. So here's a micrograph that we're looking at of a particular data set. We'll be talking about this one a little bit later on. In this image, we want to get an idea of the ice thickness. If we look at the Fourier transform of this raw microscope image, it looks like this, the right side of this plot here. The left side is the theoretical CTF after fitting, what it should look like. And the right side is what we see in the image as the Fourier transform of that image. If you look closely, you can see the tone rings at the low resolutions here. So this particular image, we don't see tone rings going out very far, which is not a good sign. What we also see is that there's this slight white band of extra density or power, in this case in the image, at a resolution in terms of Fourier space that's around 3.5, 3.7 angstroms. That white band of background noise that's present in the Fourier transform of the image corresponds to signal coming from water molecules in the ice. The reason that that signal appears in this band is because water molecules generally have a spacing in liquid phase water or crystalline ice that is not completely random and has some average distance, which is around this resolution distance, 3.5, 3.7 angstroms. It corresponds to that sort of wavelength in a spatial sense. And so when there are water molecules in that arrangement and electrons diffract from those, in each frame of the movie, the water molecules are in a slightly different position. They don't line up coherently because of the motion and everything else that we can't correct perfectly at the resolution of water molecules. And so all those water molecules from frame to frame are depositing energy in the image since the electrons are diffracting through those water molecules. That looks like a bunch of noise around 3.5 to 3.7 angstroms in all directions uniformly. And that's why we get this white band of extra background noise in the Fourier transform of the image. If you look on the left side, the theoretical CTF doesn't have that band, since the theoretical CTF isn't modeling water molecules or anything else. It's just modeling the microscope contrast transfer function. So this is something that we can't explain with our model. And that background noise is exactly what tells us how much ice there is in a relative sense. It doesn't give us an absolute measure of the thickness of the ice, but it does provide us with a relative estimate from image to image in the same sample in the same microscope. Does one image have more or less ice than another? So for example, in this job, I can just quickly find some images that have very little ice thickness. Here you see that there's almost no band at all. This is an image where the ice is obviously very thin now that we're looking at it in this way. Whereas an image with more ice has a much thicker band of power in this noise ring. So that's estimated in patch-based CTF estimation by taking, the rotational power spectrum of the 2D Fourier transform. That is this red line, fitting a background estimate, that's the black line, and then measuring how much extra background there is in this 3.5, 3.7 angstrom range.
Perfect. Thank you. Another question about CTF estimation. In the T20S tutorial, did you use dose-weighted images or non-dose-weighted images? And do we have the option to choose non-dose-weighted images for CTF estimation in CryoSpark?
That's a great question. So that's actually done all for you under the hood. Patch-based motion correction in CryoSpark creates both dose-weighted and non-dose-weighted images. If you look at the outputs tab of this patch-based motion job, you'll be able to see in more detail what are all the things that this job has created for us. The outputs are split into two sections. One is micrographs and the other one is micrographs incomplete. This is incomplete section as a placeholder in case the job is running and it fails at an intermediate point. Every 20 or 40 micrographs, it's going to be outputting information about the micrographs that it's already processed. And the ones that are not finished yet will come out in this output. So if the job dies, let's say it's a long job or a very large data set that you're processing, if the job dies, the outputs for, or rather the set of micrographs which haven't been processed yet are available from here, and you can connect them to another CTF estimation job to continue processing where the job failed if you had some kind of memory error, hardware error, etc. In the micrograph section, you can see all the outputs that are created for the micrographs that were processed. So one output is called micrograph blob non-dose weighted. That refers to the actual raw micrograph images that are created after motion correction that are not dose weighted. There's another output called micrograph blob, and this one is dose weighted. We just don't write that it's dose weighted. It's implicitly in our conventions known that this one will be dose weighted. There are also some thumbnails at different sizes, a background estimate, motion trajectories, spline-based motion parameters, and so on. And so these two outputs, micrograph blob non-dose weighted and micrograph blob, correspond to the non-dose weighted and dose weighted images respectively. When you create a patch-based CTF estimation job, if we look in the inputs and parameters section here, this job is using the data from that motion correction job. So if we expand the exposures input here, we can see exactly what was connected in all the slots. The CTF estimation job actually takes in non-dose weighted micrographs, and those came from J37, that was our previous motion correction job. It also takes in the dose weighted images and the microscope parameters. And if the non-dose weighted images are present, CTF estimation will always use the non-dose weighted images. The reason for that is that radiation damage doesn't actually change the fact that there are atoms in every frame that are refracting electrons and therefore creating signal that can be used for CTF estimation. It doesn't really make sense to apply exposure weighting where we're removing high resolution information from later frames just because of radiation damage for the sake of CTF estimation. Since we don't really care about the content of the high resolution signal, we just care about the presence of high resolution signal for estimating the tone rings. And so the non-dose weighted images are more useful for that. And so that's already taken care of under the hood.
Thank you. Going back to CTF plots for a minute, in the image where we can see all of the various tone rings, what's the difference between the left and right half of the image, if you can reiterate that?
Sure. So the image we were looking at in that case is in exposure curation, where we're looking at a particular micrograph. So when we see the raw micrograph, we're looking at the real space version of the image. So these are actually the pixels on the detector. We're looking at proteins, pretty straightforward. This image that we're looking at is a diagnostic plot for looking to see visually how well does the experimental data in Fourier space now match with the simulated CTF with the parameters that have been optimized. We should see that these rings all line up from left to right. The reason that this image is split in left and right is that the right side is the Fourier transform of the raw data. For those who are familiar with Fourier transforms, you'll know that when you have an input signal that is a real space image, so every pixel has a real space value rather than a complex number value, the Fourier transform will always be symmetric in the sense that the magnitude of the Fourier transforms on one side of the 2D Fourier transform, if you flip them over the center, will be exactly the same on the other side, which means that the Fourier transform image is actually redundant. We only need half of it, and the other half is an exact copy of the first half. And so we just don't show the left half of the experimental 2D Fourier transform. We show only the right half of it, and then we show on the left side the the simulated CTF tone rings so that we can tell how well they match up.
Thank you. Also on exposure curation, can you please clarify what are the units of the ice thickness values that are shown in this table?
Great question. They are unitless relative values. The way the whole system is set up, that the values will typically be greater than 1. A value that's smaller, closer to 1, indicates that there is no excess power in the background in the ice thickness band. A value that's much greater than 1 indicates that the power in the ice thickness is that much more than what the rest of the background is. So for example, a value of 1.5 means that this ice band has 50% more power than the rest of the background. Whereas a value of 1.0 means that we can't detect the ice band at all. So that's what's really being computed, but those units are not something you can transfer from one data set to another or really compare in any kind of numeric sense as an absolute measure of ice thickness. It's only relative between micrographs. And we'll see today when we go into detail in tilt data and exposure curation exactly how useful that is and how it can show us the difference between good and bad ice.
Later on today, when we go more in depth on exposure curation, will you be able to show us if we can sort or automatically remove images that have too much ice or where the ice is too thick for that image?
That's exactly what we'll be doing. Yep.
Perfect. In the interest of time, I'm going to move ahead to some questions on 3D reconstruction.
Great.
When it comes to ab initio reconstruction, where we're using more than one class, what similarity, class similarity specifically as a parameter, should we choose between the classes?
That's a great question. I'm going to address that in particular in the upcoming section where we'll go in depth into multi-class ab initio reconstruction, dealing with heterogeneity for interesting data sets.
Thank you. And during that time, will we also cover the topic of knowing how many classes to ask for in ab initio reconstruction where you expect heterogeneity? Perfect.
Definitely.
Thank you. All right. Okay. In the case where, and this is now again dealing with heterogeneity. So in the case where we have both a liganded and unliganded protein in our sample, is heterogeneous refinement better than homogeneous refinement?
Yes, in a sense. So in a case where you have a ligand, where you have a sample that has both an unliganded and a liganded version of your structure, what you need to be doing is trying to separate those two conformations via classification. Now, how exactly you do that and how effective you can be at that depends on a couple of factors to do with the actual protein. The most important one is whether or not the binding of the ligand causes any conformational change throughout the rest of the protein. Generally speaking, if the ligand is, and this is just conjecture, but if the ligand is doing something interesting, it is likely to cause some kind of conformational change that affects the functioning of the rest of the protein. I mean, that's not always necessarily the case, but that's often the case. When that is true, it's much easier to detect the presence of the ligand because you don't actually have to detect the ligand itself. You can detect the conformational change that is caused by the ligand, and that's usually a much broader, larger scale change. It doesn't have to be a huge amount of motion, but more atoms in the protein are literally moving. And so that, when it comes to classification, what you should think of intuitively in terms of how to tell whether a classification is easy or hard in terms of signal is how much mass or how much electron density, Coulomb potential, whatever you're going to call it, is changing from one state to the other. So if you're working with a large protein, tiny ligand, and there's absolutely no difference in the structure between the bound and unbound state, it's probably very difficult to classify those two out, because the only signal that's present between one single particle image and another to identify the presence of the ligand is the ligand itself, and that's just a few atoms. With the noise levels that we have, it's pretty much impossible to tell that it's there or not. On the other hand, if the ligand does something by changing the conformation of the protein and the rest of the protein actually moves even a little bit, that change can be totally detectable because the total amount of mass that's moving or changing is much larger. So in terms of the actual strategy for how to do this, in cases where you're looking for nuanced conformational differences, there are two strategies that you should use. One is to use heterogeneous refinement as opposed to ab-initio reconstruction. Ab-initio reconstruction for solving heterogeneity problems is really aimed at the case where you have multiple very distinct, or at least grossly different conformations, maybe even totally different particles, conformations or subunits missing here or there, large changes that where your different structures are not similar to each other. That's really the most powerful case for ab-initio reconstruction. It can work in other cases too, like we saw with the ATPase molecule. It can detect the rotation of the central stalk, which is not a gigantic change in the structure of the protein, but it's not small. On the other hand, if you're looking for smaller changes, heterogeneous refinement specifically is built for that case where it is allowed, or it is able to do classification of the images at a much higher resolution than what ab-initio reconstruction can. Ab-initio reconstruction, if you remember, in our default parameters is limited to a resolution of around 8 to 10 angstroms, or 12 angstroms, I think even was the default. And so at 12 angstroms, you really can't see small conformational changes. With heterogeneous refinement, the conformational changes are detectable at whatever resolution the data allows, because heterogeneous refinement is going to be estimating resolutions and refining the structures to high resolution while it's classifying. And therefore, it can classify at 3 angstroms, 4 angstroms, 5 angstroms, depending on the number of particles and the quality of the data, of course. So what you should do in the case of looking for small conformational changes, one strategy, do an initial reconstruction, an ab initio reconstruction with one class, a refinement with one class, and get a high resolution version of the consensus structure, which is going to be an average of the two conformations that you're looking for. And then take all of those particles and that initial model and feed them into heterogeneous refinement, looking for 2, 3, 4, however many different conformations you want to ask for. Heterogeneous refinement is then likely to separate that into subpopulations of slightly different conformations, which may find you the bound and unbound version of the protein. The second strategy, which I would even more highly recommend, is something that we're going to go into detail in later on today, which is to use the new 3D variability analysis algorithm that's in CryoSpark. 3D variability analysis is something that we developed very recently, and we have a paper that just came out a couple of months ago on bioRxiv describing the algorithm. It's a new technique that doesn't work the same way as previous classification techniques, but can directly resolve small and including very small conformational changes, even continuous flexibility within proteins, even at high resolution. And so if you're looking to distinguish between bound and unbound states with a ligand, I would suggest taking all the particles and putting them to 3D variability and see whether 3D variability can separate the two states, which is, I feel, much more likely than any other strategy.
Perfect.
Sorry, long-winded, but yeah.
Thank you. No, I think that was really helpful. Just to wrap up this section before we head back into the general webinar portion, we had several questions about how to interpret plots in ab initio reconstruction and refinement. We will be going through all of those plots in more detail today as we process more data. So we'll be sure to go over all of the details at that time. I'm thinking about things like orientation distribution plots, Gunier plots, etc. So we'll cover all of that today. Just a final question for heterogeneous refinement. Can we use the same model as multiple inputs for heterogeneous refinement? And the short answer to that is yes, you definitely can. And I believe we will actually be going through an example of that later today as well.
We won't actually be using heterogeneous refinement. I can show how to start off the job. We won't actually be using it in the practical. But yes, the short answer is you can input the same initial volume multiple times into heterogeneous refinement to instantiate multiple classes. You can also input multiple different initial volumes if you want to do that kind of classification as well. When you do input multiple of the same initial volume, the first step of heterogeneous refinement breaks the symmetry in the sense that it adds some, it chooses a set of random particles for each of the identical input volumes and reconstructs a slightly different version of the input volume so they're slightly perturbed, and that's what allows them to converge to different solutions at the end. If they all started exactly the same, then all the particles would classify evenly into all the initial models, and so that's obviously a problem. But that's taken care of under the hood, so you can connect in multiple copies of the same initial volume.
Great. Thank you so much. I think we're right at about time to get started again with the rest of the webinar. And we'll continue to take questions as we did yesterday at specified points after each substantive topic in the lecture.
Great. It looks like we're up above some 250 participants, so I think we're ready to continue. Before we begin, I just want to let the practical participants know that you have all been sent the day 2 practical instructions this morning, just to make this whole process a little bit easier. So you can follow along with those instructions. I will also be doing each step right in front of you here, so that makes it a little bit easier as well. But in case you fall behind or want to go ahead, you have the instructions ready for you. 2 notes about that. When you're doing the practical, please make sure that when you're processing each data set that we go through today, you're making a new workspace inside of the same project that you used yesterday. Don't make new projects. And that's not a rule generally for CryoSpark, just for the practical purposes because of the way the file system is going to work. And secondly, note down your project number. So for example, on this instance of CryoSpark 01.slack, my project number, Ali S2C2 processing, is project number 6. So note down that P6. You'll need it for some of the import jobs that come later. Okay, to get started, I am going to actually start off one of the new data sets that we're going to process today, just so that the jobs are running behind the scenes before I start getting into detail, into a lot of details about various topics. So the first data set that we're going to be experimenting with for the purposes of understanding how some advanced parameters of motion correction, CTF estimation, how to do exposure curation, how to deal with tilted data and preferred orientation is an interesting data set. It's a hemagglutinin trimer data set that was collected at the New York Structural Biology Center. What's interesting about this protein is that it has a very strong preferred orientation when you create standard grids with the standard sort of blotting techniques. What happens is that the trimer stands up in the ice, and all the views that you see, if you take conventional images, are top views. You see only views from the top. And that makes it very difficult to reconstruct a 3D structure, since obviously you don't have any side views or information about the overall structure. So the solution to this problem that was put forward in the original paper where this structure was solved was to tilt the stage during data collection. Now, tilting the stage adds a whole lot of complications, and you can imagine some of them if you were listening to our presentation yesterday about CTF estimation and motion correction. We know that in motion correction, what we're trying to correct for is in-plane sample deformation that we can see when we're looking down on the sample. The ice is bending, and we're trying to track that motion in the XY plane. But when we tilt the sample, all of that sample motion and bending of the ice and doming of the ice now appears, instead of going up and down along the direction of the beam where we can't see it and it doesn't cause motion blur, it's now out of plane, or rather in plane, and it's the motion of the tilted ice is now moving with respect to the electron beam. And so the amount of motion and the degree of motion is extremely large with tilted data. So that creates one big problem with motion correction, is that the motion can be very jagged and have huge bursts as the ice first starts to bend in the first few frames. And also we'll see lots more anisotropic deformation of the ice because of the tilt. So dealing with that is one issue. The second issue is that we know that CTF estimation needs to accurately get the defocus of each particle. In tilted images, by definition of the tilt, particles on one side of the micrograph are higher in the electron beam than others, and therefore closer or further away from focus. And so we can definitely no longer assume that the ice is flat. We have to use something like patch-based CTF estimation to get an estimate of the defocus at every point in the ice. Previous techniques for dealing with tilted data have revolved around either the user inputting the level of tilt and the direction of tilt, or having some methods to try and estimate that. And that can be error prone, since not every image may be tilted by the same angle. There may be residual tilt in the crinkling of the grid, and so on, all kinds of other issues. So we kind of want to avoid that picture as well. So dealing with tilted data, and in this particular data set, is a bit of a challenge. Luckily for us, it turns out that it can be done very easily. We're not actually going to go through the full 3D reconstruction of this data set. We're just going to do the motion correction, CTF estimation, and curate the data. The reason for that is that this data set is also interesting in the sense that it has different segments that were, as it was collected in order, different parts of the grid that were better and worse. And we can detect that using exposure curation and, for example, ice thickness measurement. So that's what we're going to try and do. So switching over to CryoSpark right now, we're going to create, if you're logged into your CryoSpark instance, which all the practical participants should be, and for those who are just watching remotely, you can just follow along with what we're doing. The instructions are also written here. And we will send these instructions to everyone, including the viewers who are not part of the practical. What you can do is first create in your project. So right now, if I go back to the beginning of CryoSpark, I'm at the dashboard. I can enter the projects page, find my project, project 6, enter that project. And now I see my workspace from yesterday, my T20S processing. Now I can click add to create a new workspace. And now I'm going to call this HA Primer. So now I have a new workspace, workspace 2. I can enter that workspace and see that I have no jobs in there. The first job I'm going to create by clicking on the job builder is an import movies job. Import movies. Now I have, by clicking on that button, I now have a new job here, job number 4. I should note that job numbers are always unique within a project. So even if you have multiple workspaces, job numbers will continue to increment based on the previous jobs that you've run in the same project. So don't be alarmed if it doesn't start at 1. Right, okay, so that is the import job. Now the parameters of the import job, we want to set the movie data path by clicking on the browse button and going to the /scratch/training /scratch/training directory. And you can get there by just typing /scratch. You'll see what's there. You can click on training. And then you can see what's inside of training. We want to go into the Slack workshop data project or directory, sorry. And then we'll see a listing of the different data sets that we're going to be working with today. The one we want to use is number 5, HA Trimer. Inside of there are a collection of movie files in a format called .mrc.bzip2. This is just one example of one of those movie files. I should mention that CryoSpark supports multiple movie files, MRC files, so those are uncompressed, just raw binary 3-dimensional volumes of frames in a movie. TIFF files, which are compressed in LZW compression, still storing that binary image data, as well as mrc.bzip2 files, which are the same as the MRC files, but just compressed afterward with bzip2 compression. That can be useful for image data that's been collected in, again, non-gain corrected, where the gain correction files stored separately. And the MRC files are just integer counts. bzip2 compression can be very effective. So for example, in this case, one movie is 430 megabytes, whereas the original MRC files were 2.7 gigabytes each. So this helps a lot in reducing the file size. What we're going to do here in the HA Trimer directory is select only the star.bzip2 files. Since we only want those as our movies, you should see 100 items. We're dealing with a subset. The original data set has some 600 movies, but just to keep things fast, since we don't need to look at all of them to study what we're learning here today, we're going to be dealing with just 100 of them. So we can go ahead and click select once you've typed in star.bzip2 here. For the gain reference path, we then want to find in the same directory an MRC file that doesn't have the bzip2 ending. So to find that easily, I just typed star MRC here, and the listing showed me this MRC file, but I need to select that file so that the full path of that file shows up here. That's our gain correction file, and then I can click select. So now we've set up our movie data input and our gain reference path. For this data set, it turns out that that gain reference is actually upside down. As I mentioned yesterday, it's common, depending on how the data collection is done, for the gain reference to be rotated or flipped or somehow not in the same orientation as the images. So we need to check this flip gain reference in Y box, and then enter the rest of the parameters for this data set. The pixel size being 1.31 angstroms, accelerating voltage 300 kilovolts, spherical aberration 2.7 millimeters, and the total exposure dose 82 electrons per square angstrom. The rest of the parameters we don't need to check. In case we were dealing with negative stain or faceplate data, we could set that here. We could also provide an override for exposure groups, which we'll talk about later, that are helpful in doing CTF refinement of multiple beam shift images. So we can go ahead and start off that import job, which will just load up a few movies, make some plots, and make sure that all the headers are fine. The next thing we want to do is go over to the job builder and create a patch-based motion correction job. And here, like I said, for tilt data, generically, we have to be worried about motion correction being difficult due to the tilt. However, CryoSpark's patch-based motion correction is specifically designed to deal with this kind of tilt data without any changes in parameters. And you don't even have to specify that this is tilted data. You can just provide the data. Patch-based motion will estimate the trajectories in the standard way. And there are some parts of the algorithm that help it to deal with very large amounts of motion and accurately track those. And those are engaged by default. So we can just go ahead and connect the output of our import job to the movie's input of our motion correction job. And we don't need to change any of the parameters in motion correction, but I'm just going to describe a few of the more advanced parameters right now, since we're here. The first few are just about plots and stuff like that, so we don't need to worry about those. One of the important parameters is the maximum alignment resolution for motion correction. This controls how far in resolution do we look when we're comparing different frames of the movie. Very high resolution information like beyond 5 angstroms is generally not useful for motion correction, since we don't expect that within a single frame we can actually see anything beyond 5 angstroms. Even up to 5 angstroms is difficult to imagine that we can see that far. But beyond 5 angstroms, it doesn't really make sense to consider that very high resolution detail during the motion correction at this stage. What we're really looking for motion correction to do is, in each frame, which is extremely noisy, see the low resolution overall shape of a particle and track that over time and align the particles based on their low resolution position. And that alignment will also align the high resolution details that we can't see in each frame. There's also a parameter for B factor during alignment. This is a blurring B factor for those who are familiar with B factors. I would generally not recommend changing this parameter, but it's something that you can use in some cases if you want to further downweight or upweight high resolution details during the motion correction. We mentioned already yesterday the start frame and end frame that can be used for cutting off the earlier or last frames. I wouldn't recommend doing this in most cases, but sometimes you can. There are some cameras and software where one or more frames can be corrupted or otherwise difficult, so you can cut those out automatically. The most important parameter that you may wish to change, by the way, I should have mentioned that for anybody who's trying to follow along here, you should always make sure that you have the advanced mode switch on in the job builder, since I'm going to be talking about pretty much all the parameters, or at least some of the advanced parameters. So the output Fourier cropping factor is something that you can choose between 4 settings. And this controls the downsampling that's going to be applied to the image after motion correction. So we take in the raw data, whatever pixel size and frame size. Let's say it's super resolution data on a K2 camera. That's going to be about 8,000 by 8,000 frames. Sorry, 8,000 by 8,000 pixels per frame. At that size and with super resolution data, generally speaking, we don't expect to resolve information beyond half of the Nyquist rate for that super resolution data, since the physical pixel size of the detector was only a certain amount, and super resolution is kind of imagining that there are subpixels when there really aren't. So what we can do in that case for super resolution data is we can downsample the images right after motion correction. The motion correction is still done with the full resolution images, but when we output the micrographs, they can be stored, they can be outputted at either the full size of the input data, 3/4 of the size, half the size, or 1/4 of the size. The most common setting is probably half in case you're dealing with super res data. In some cases, you may want to choose another one. Really what this affects if you're dealing with super resolution data is that with super resolution data, sometimes you can get a 3D reconstruction that goes slightly beyond the physical Nyquist rate of the sensor because you had super resolution data. In most cases though, the quality of the signal beyond the physical Nyquist rate of the camera drops off very fast. And so you can only expect to get a little bit beyond the physical Nyquist rate. However, if you do collect in super resolution mode, doing Fourier cropping can help resolve high resolution details that are close to the Nyquist rate of the physical sensor by stopping aliasing artifacts that would have happened if you hadn't collected in super resolution mode. So the short version of that is you can sometimes use Fourier cropping if you want to downsample the images right at this stage. That way, the images will be smaller particle box sizes will all be smaller. Everything will be computationally easier and faster, and disk space will be less wasted, and you won't lose very much in that case. So that's the Fourier cropping factor. You can also override the electron dose that we talked about yesterday. And I won't go over any of the other parameters except to say that these motion correction jobs and all pre-processing jobs in CryoSpark are parallelizable over multiple GPUs on the same node. So if you have, let's say, 4 GPUs in a worker node, you can have all 4 of them performing motion correction on the same data on the same set of movies at the same time, and that can provide basically a linear speed up for pre-processing jobs. I'm not going to do that right now, though. We can just go ahead and queue this motion correction job. I'm actually not going to queue it here since there are others using this particular node, and they should use those resources. I'm going to switch over to my own instance of CryoSpark where I've already run that motion correction job. The next thing we want to do is CTF estimation. So actually coming back here.
Just going to interrupt for 1 second on a point of clarification. In our patch motion job, we set the parameter maximum alignment resolution. So the question is, if the motion is more than 5 angstroms, those images will be selectively removed or not processed at later steps. Is that correct?
No, I should clarify that this parameter doesn't control the maximum amount of motion that we can consider. Generally speaking, we can track motion of dozens or hundreds of angstroms even for very large motion data sets like this one. What this parameter controls is the resolution of the image that we consider during motion correction. So for example, when we're looking at frames of the movie, when this setting is set to 5 angstroms, we don't look at resolution information, high resolution details beyond 5 angstroms in the frames when we're doing the motion alignment. The actual motion trajectory can be much larger than 5 angstroms, but we don't look at, let's say, 3 angstrom resolution detail when we're tracking the motion. Since from frame to frame, we can't trust that very high resolution detail anyway. There's just so much noise in individual frames of a movie since the electron dose per frame is so low. Hopefully that.
Thank you. 2 more points of clarification for those in the practical. How many movies should we expect to see in our HA trimer data set?
100.
100, thank you. And the number of movies to plot parameter, is that by default set to 10 or do we need to change that?
No, that's by default set to 10. One thing you should know about the job builder in CryoSpark is that every parameter has a default, and when the parameter has taken on its default value, you'll see this little blue D beside the parameter name. When you do change a parameter, let's say I change this to 3 angstroms, that parameter will turn into an S, or a specified parameter. That's an easy way for you to track which parameters are non-defaults for a given job type. You can also clear a parameter setting by clicking the X, and that'll set the parameter back to its default.
Perfect.
So right now, I haven't changed the parameters at all.
Perfect. So we're keeping all of the default parameters for the practical participants. Thanks.
That's correct, yeah. So while this patch motion job is running for the practical participants, we can also go ahead and create a CTF estimation job, patch-based CTF estimation, once again. We can take the outputs of our motion correction job, the micrographs here, and connect them to our CTF estimation job. And once again, in this job, we're going to use the default parameters, but I'm just going to go in a little bit of detail to explain some of the more interesting ones. Like I was explaining earlier, with this tilt data, we ordinarily would be concerned that CTF estimation would be difficult because of the tilt. But CryoSpark's patch-based CTF is specifically designed to measure or estimate a defocused landscape for the micrograph. And it turns out that it can do so simply right off the bat. And it can detect the tilt of the ice because of the gradient of defocus from one side of the ice to the other. Without knowing the direction of the tilt or the amount of tilt, it can recover those directly from the image data for us. And that makes processing tilt data really, really easy. It basically means we have to change nothing in our workflow. We just import the data, whether it's tilted or not, use the exact same processing, and we're good to go. But we can deal with preferred orientation much more effectively with tilted data. So in the CTF estimation job, again, when we're running it for practical participants, you can go ahead and queue the job because we don't have to change any default parameters. But just so I can explain what some of the parameters do, the first one is amplitude contrast, and that is a fixed value typically for the type of imaging that we're doing, 0.1 for cryo-EM data and 0.3-ish for negative stain data. It corresponds to our notion of how much of the contrast in the image is being formed by amplitude contrast versus phase contrast. We talked earlier and we saw in yesterday's morning lecture that the images that we collect are collected in phase contrast mode. And so we expect that most of the contrast in the image is coming from interference patterns, phase contrast. However, there is some component of amplitude contrast due to various other electron phenomena that we won't get into. And for negative stain data, it's better to use a larger number here, like 0.3. When you import negative stain data, CryoSpark will automatically set this parameter to 0.3 for you. The other parameters are the minimum and maximum resolution to consider for estimating the CTF. We talked about this yesterday as well, and this determines which section of the 2D Fourier transform we're actually going to look at for fitting the tone rings. At very low resolution, there aren't any tone rings, so we want to ignore anything worse, anything lower than 25 angstroms. And at very high resolutions, the images are dominated by noise, and so we don't want to consider that for fitting the tone rings either. So generally speaking, these parameters work very well. You probably don't need to change them. The minimum and maximum search defocus range we also talked about as being the range of defocus values that we can consider. If you collected images with a very high defocus, you should change this number. And I won't talk about any of the other parameters right now either. So we can go ahead for practical resistance and queue this job, which will do CTF estimation on all 100 images. Okay, so that's enough setup for the HA trimer, and we've been able to go over advanced parameters of motion and CTF to some degree. What I'm going to do next is, while this stuff is processing for our practical participants behind the scenes, we're going to go through some more slides that show us that we're going to pick up basically from where we left off yesterday at the end of 3D reconstruction. I talk about a few more topics: measuring resolution, local resolution estimation, overfitting and preventing overfitting using gold standard Fourier shell correlation, orientation distribution plots, and so on. And then we'll come back to CryoSpark to look at the results of our processing and do some exposure curation on the HA trimer dataset. Okay, so moving over to the next slide. The next topic we're going to start talking about is how we measure resolution in single particle cryo-EM. Resolution estimation and validation of a cryo-EM structure is a very important topic, and we're going to have, I think, a longer lecture about this tomorrow. But just to give an idea in practice of what is done, in order to measure resolution of a cryo-EM dataset, we don't have any ground truth measurements. We don't actually know the structure of the protein, and we don't actually know the alignments of particles in any given single particle image. So we can't directly verify that the structure we've solved is actually correct. The two ways to verify that a structure is actually correct are, one, to convince yourself that it's correct because you see structural details that you believe could only appear if this was actually a correct protein structure. Like if you're looking at side chains, or I mean, at very high resolutions, you can identify particular aromatic rings or whatnot. And then you can be quite sure that this is a correct structure, or by doing a statistical test to tell whether or not you can statistically believe that the structure that you've solved is reproducibly validatable from the data that you've collected. And that's as much as we can say. We can't definitively say that a result is absolutely correct compared to the real cryo-EM structure. We can just say that up to a certain resolution in this data, the data suggests that statistically we can trust the structure up to a certain resolution. And that's what resolution estimation is really about in cryo-EM, is about validating whether or not, how far we can trust the result that we have. The way it's done in practice is to take your data set and split it in half. By splitting it in half, we've now introduced a cross-validation notion where we're resting on the fundamental principle that we expect all of our image data to have come from the same generative source, which is the real protein molecule, and in the same imaging process. So any particles that are on one side of the split have the same information content as particles on the other side of the split, but particles on both sides have different noise content. So the things that we want to believe are things that are in common between the two sets, and the things we want to ignore are what's not in common between the two sets. And that's exactly how validation in cryo-EM works. So the data set is split in half, and then we do a full independent refinement of both halves separately. So the particles don't see each other. We don't use the same particles and the reference from the opposite half ever. By doing that, we get two independent refinements, two fully separate 3D reconstructions, and then we compare those in Fourier space. We take the Fourier transform of the two refinements, and we end up with two Fourier space structures, essentially, where we have values for Fourier components at different resolutions. At the center, we have low resolutions. At the outer edge, we have high resolutions. And at a certain point, as we move further away from low resolution towards high resolution, the two structures will stop agreeing with each other. And that's what we want to measure. The way it's done in practice is by using something called Fourier shell correlation, where we literally take shells, so like spherical shells of Fourier space that have the same resolution but in different directions, and compare those shells from one half map to the other. Where the two half maps have the same content in those shells as measured by their correlation, we literally plot that correlation value, which takes on a number between +1 and -1 as a function of resolution. And that's what the FSC curve is at a simplistic level. The FSC curve provides information about how well the two half maps match up as we move to higher and higher resolutions. And at a certain point, the FSC curve drops to a low value near 0 and starts to wander around 0. At that point, we know we can no longer trust the data. Now, I'm not going to get into how we define a threshold or how we decide what's a statistically significant FSC versus not. Suffice it to say that most people use a threshold of 0.143 correlation. I won't get into the reasons why that's the case, but it's derived based on some principles. And that value is where we say that beyond this resolution, where the FSC drops below that number, we can no longer trust the structure. At resolutions worse than that resolution, we can trust the structure because our correlation between the half maps tells us that that content, signal content, is actually present in the data and is not part of the noise. One thing about the Fourier shell correlation is that when we compute it, it depends heavily on a mask, the mask being a solvent mask that excludes parts of the 3D volume in terms of the actual voxel grid that are outside of the protein. So that's basically solvent. By masking out the solvent, we remove all the noise from the solvent in both half maps, and that strengthens the relative strength of the signal from the protein itself. So if we compute an FSC without any masking, that's this blue line here, we get a very low FSC curve. As we use a mask that becomes tighter and tighter around the protein, removing more and more of the solvent, the green line, for example, is just a spherical mask that cuts out the corners of the 3D box. So that's very loose. That's already creates a substantial difference to the FSC. And if we use a mask that is shaped the same shape as the protein, but is very loose, that's the red line, loose mask, then we get an even better FSC. And if we use a tight mask, which is the same shape as the protein, but comes closer to the edge of the actual protein density, not too close, and we'll get into that, then we get an even higher resolution estimate. It's important that we don't mask too much because then we're going to be cutting into the protein, and that cutting causes a correlation between the two half maps that is not true. And so to make sure that that's not happening, there's a technique called noise substitution correction, or a noise substitution test, where we can tell whether or not the FSC curve is reliable by computing the corrected version of the FSC curve. And as long as the tight and corrected versions of the FSC curve are close together, we can trust the corrected resolution of this FSC estimate. That's what we do in practice in CryoEM. So in each refinement job, we actually produce this entire FSC plot at each iteration, computing all of the FSC curves with different shaped masks so that we can watch the progress of those as we refine the structure. Okay, so that's resolution estimation. I'm going to go and show some of the detailed plots in a 3D refinement in a moment. But before that, I'm just going to explain a few more concepts. Related to resolution estimation is the notion of local resolution. Local resolution is kind of a fuzzily defined concept. It intuitively is supposed to capture the notion that in a 3D protein structure, when we're solving it, due to various factors, whether it's disorder, rigidity, flexibility, whatnot, or partial occupancy, some parts of the structure will be better resolved than others. And that's a very common thing. Local resolution estimation is the idea that we can somehow measure the local resolution to which we can trust the structure in a particular area. There are multiple different ways of computing a local resolution estimation. In all cases, the local resolution values themselves, the actual numerical values, are not to be trusted as somehow telling us that we can definitively trust information in a particular part of the structure to a particular resolution. That's not part of what local resolution estimation does. It's not a validation measurement. It is a qualitative measurement to show us which parts of the structure have relatively better or worse resolutions. the simplest way to compute it, and what's done in CryoSpark, but just fast on GPUs, is to just crop small volume boxes at different regions of the protein, slide that window over, and for each one, compute the standard FSC and get a resolution estimate for each little region of the structure. That's what allows us to create these colored plots. So this plot, this density map, is colored by its local resolution value. Like I said, you shouldn't trust those numerical values, but they can give you an idea of the difference between some regions and others. Typically, the core region of a protein that has more protein mass around it will be more rigid and higher resolution and so on. So those job types are available in CryoSpark as local resolution estimation. You can also filter a 3D structure by its local resolution, and that's a slightly more advanced way to just visually help distinguish regions that are more or less resolved. The next topic I'm going to talk about is also connected to resolution and trusting a 3D structure, but it's a slightly more nuanced topic that ends up being very important in practice. And it's the notion that when we do a refinement, a 3D refinement, or any kind of refinement actually, the process that the problem that we're trying to solve is an estimation problem, an inference problem. We're trying to infer the 3D structure of the protein from the image data. But we don't actually know how much of the image data we can trust. We also don't know whether or not we're on the right track. We talked about this already with Ab-initio reconstruction. But the most important principle that we need to consider is that in any estimation problem, inference problem, it's very easy to, as you're optimizing the 3D structure, for example, that we're looking to solve, over-optimize it to the point where parts of the model that we have, for example, the 3D structure or the alignments of the particles, are driven not by signal in the images, but by noise. And as that noise in the images causes slight mistakes in estimating alignments or reconstructing the 3D structure, those mistakes in this iterative loop between alignment of a particle image to a 3D structure and then reconstruction of the 3D structure from all the particles, as we iterate that, this way over and over, small noise and small errors can accumulate and start to build up. And we call that overfitting. And that's a generic concept that actually applies to all kinds of machine learning and estimation problems and inference problems of any type. And it's really a fundamental concept when it comes to sort of information theory. We can't tell the difference without some special techniques between real things that we're inferring and things that we've overfit because our data set is limited in size or there's noise in the data. If we refine too much, we end up with overfitting. And this used to be a very difficult problem in single particle cryo-EM and something that has been addressed by many people in the field. Today, the probably most commonly used, if not most widely accepted in the methods community, technique for combating overfitting during a refinement is to use the notion of resolution estimation as a way to tell us how much we can trust the 3D structure at every iteration of refinement and only allow ourselves to trust the structure to the point where we can validate that it's trustworthy. What that means is that previously I mentioned that what we do in measuring a resolution at the end and validating it is split the data set in half and do 2 independent refinements. What really happens under the hood when we're using a technique like this is what's called gold standard FSC, is that the data set is split in half. And we start with an initial model at a low resolution. Then we start to compute iterations of refinement. So we do alignment of the particles in half set A and recover a structure, do alignment of particles in half set B, reconstruct a structure. Both of those structures will now be a slightly better model of the protein. But instead of trusting everything that we just inferred at this one step, we compute the independent, we compute the FSC at every iteration between the 2 half maps. And that FSC curve tells us how much of the structure on both sides we can actually trust at every iteration. And therefore, at every iteration, we can remove information in the half maps that's not present, not really signal, but actually noise. And by doing that, what's known as regularization of the problem, we can arrive at 3D structures that converge correctly and don't overfit, generally speaking, and actually pretty much always don't overfit. And we can then still validate the final resolution using the technique I mentioned before, which is the Fourier shell correlation curve. So doing these independent refinements is all part of the gold standard FSC, and filtering in between iterations is a technique that allows us to regularize 3D structures and prevent overfitting. And this is a concept that will come back as an important notion in what controls the quality of a 3D reconstruction at the end of the day. Finally, the last topic I'm going to talk about before we look back at CryoSpark is orientation distributions. We've already talked about how important orientation distributions are in terms of recovering 3D information. And I just want to explain some intuition about how you can think about orientation distributions. In CryoSpark, we plot them so that they're a little bit easy to interpret as a flattened globe projection of viewing direction. So if you think of a 3D structure, you can look at it from all different angles. You can also, when you're looking at it from a particular angle, rotate the camera in plane so that the image just spins around. We don't really care about that since the content of an image rotated in plane is the same. What we care about are the 3D viewing directions. So what we plot in this globe projection, this flattened histogram, is the number of particles at every different azimuth and elevation viewing direction. So azimuth is going around the structure, like along the equator, and elevation goes between 0 and 90 degrees towards the poles. What we will see in this plot is a sort of spread out histogram of the viewing directions, the distribution of viewing directions of the particle images based on the estimates of their alignments that we have from a refinement. What we want to see is a good coverage of orientation space. We want to know that we have seen the 3D structure from enough different viewing directions that we can actually reconstruct and believe the 3D structure. Now, what's really important to think about here is that intuitively, you may think that based on this plot, what we're looking for is uniform coverage of all orientation views. That's not true. We don't actually need every viewing direction. What we need is a certain set of viewing directions that collectively give us enough information for a 3D reconstruction. And this is kind of a nuanced topic. The way you have to think about it geometrically is that we don't necessarily need to see every direction, but enough directions to cover 3D Fourier space. And I'll explain what I mean by that. We heard in yesterday's morning lecture that one of the concepts that allows us to do a 3D reconstruction is the Fourier slice theorem. What the Fourier slice theorem says is that if we're looking at a 3D structure and we project it along some direction to get a projection image, like what we observe in the microscope, ignoring the CTF and other things right now, we get this projection image that is a picture of the structure from a particular direction. And from that direction, this projection image contains information, partial information about the 3D structure. We've lost all the depth information along the ray of projection. And in Fourier space, if we think of the Fourier space version of this 3D structure, what we've observed is all the Fourier components of a central slice through the 3D Fourier transform of the structure. So this 2D image that we get in the microscope gives us information about a plane in the 3D Fourier space of the 3D structure. All of the different images that we get from different viewing directions will touch a different plane in 3D Fourier space. And what we need is enough viewing directions that every part of 3D Fourier space has been covered to some degree. We don't actually need to see every viewing direction. So a good example of this is this ATPase molecule. It is sort of dumbbell shaped. And when it's in the ice, it generally likes to lie down flat. But it will rotate. It'll have lots of equatorial views. When we see it in the ice, we'll see it from all different angles around the equator, around the axis, the long axis of it. And we'll sometimes rarely see it from the top or the bottom. And we'll almost never see it from oblique sort of diagonal views. That's what this orientation distribution plot suggests, that for this structure, we have this band of views that are kind of in a sort of tilted equatorial plane. And then we have a few views. By the way, this is a log histogram. So as the colors get more red, this is increasing in log units. So a red square has 100 times more particles than a blue square. So we're also seeing a few images from sort of top-ish and bottom-ish views, but we don't see every different viewing direction. But this is enough, because if we think of a structure, if you look at it from all different side views, if you think of what one side view represents in Fourier space, it's a plane that's aligned with the vertical axis. And every different side view is a different plane that's aligned with the vertical axis. All of those together actually are enough to touch all of 3D Fourier space. So theoretically, we don't need more views than what we get in this case. We need a few top views and a few bottom views to help us figure out which plane is which around the equator. Like for example, with the T20S proteasome that we processed yesterday, we get lots and lots of side views. Those are all equatorial views. And then we get a few top views. If we didn't have any top views, it wouldn't be easy to reconstruct the structure because there's no information that shows us that the structure has, for example, this 7-fold symmetry. In a side view, you can't see that. So with a few top views and a bunch of side views, there's enough information to recover the 3D structure, and the side views actually touch all of Fourier space, so we can go to very high resolutions. That's what we kind of need to intuitively keep in mind when we're thinking about orientation distributions. What you don't want to see is an orientation distribution where you only have one major hotspot of views, or maybe two. That's not enough views. If you only see a 3D structure from two directions, that doesn't cover all of 3D Fourier space. You need a nice spread of views. And tilting the image, tilting the data set tilting the sample helps a lot in that case. Like for example, with the hemagglutinin trimer, if you think of that structure, it's this trimeric protein, and we can always see it from the top if the sample is flat. But when we tilt the stage, all the top views become sort of oblique. And because the protein exists in many different orientations in the ice in the vertical axis, when we tilt, we end up seeing many different orientations around and close to equatorial, well, sort of elliptical band of views. Hopefully that's making sense to everyone who's watching, but that's kind of where we need to think about what we need to think about for orientation distributions. So at this point, I'm going to switch back to CryoSpark to go through some of the plots that come out of a 3D refinement and also Ab-initio reconstruction, so we can explain how to understand those diagnostic plots. We already talked about motion and CTF advanced parameters, and we'll start to do our hemagglutinin dataset curation so that we can see what it's like to separate good and bad data.
We have just a couple of theoretical questions on validation, and I don't want to go too much in depth because we have a whole morning session tomorrow dedicated to the topic, but just to clear up some of the questions right now. Sorry.
No problem.
What is the significance of the Fourier shell diameter, the yellow circles that you were showing on one of the slides?
Let me just go back there.
Yep.
I'm guessing the questioner is referring to this yellow circle.
Yes.
I'll answer both questions that have a circle. So the black lines are just examples of different shells at different resolution values. This is not to scale or anything, but just a diagram so that you know what's happening. The Fourier shell numbers at lower resolutions correspond to smaller shells near the origin of Fourier space, which are corresponding to low resolution details of the structure. And the larger shells are high resolution details of the structure. The yellow circle here is just a part of the diagram. When we did the 3D reconstructions of these two half maps, the yellow circle was the resolution limit of those. And so beyond that, we don't have any information anyway.
Do we know anything about the percentage of data in each resolution shell?
Percentage of data in each resolution shell. I'm not entirely sure if I'm going to interpret this the same way the questioner was asking it, but each resolution shell gets the same amount of data in the sense of the number of images that contribute to it, since every image is a plane in Fourier space. And so every image is touching all the Fourier shells. What happens is that the number of Fourier components as you go to higher resolutions gets larger and larger. It's like the surface area of a sphere. So it's quadratic. And so the number of different Fourier components that you have that you need to get information from the images increases very fast. And that's why for very high resolution structures, we need lots of image data, because as we go to higher and higher resolutions, there are more and more Fourier components that we need to fill in by having observed them in multiple images to be able to reconstruct those. So hopefully that answers the question.
And finally, what is the y-axis on the FSC plot? What does that
Sure.
mean?
The y-axis is literally the correlation. If anyone remembers like a Pearson correlation coefficient or a normalized correlation coefficient, literally you take all the Fourier component values in one shell and all the Fourier component values in the other shell. You take the inner product of those two, so you multiply them correspondingly and add that up, and then you square the ones on one side and add that up, and square the ones on the other side and add that up, and then divide those to get the normalized correlation. And that's a number that's always between +1 and -1. We don't really care about values below 0, since that indicates that the Fourier shells are anti-correlated, which would indicate something very bizarre, but we generally don't, that doesn't help us. What we want to see is that the correlation is close to 1 or greater than 0 by some significant amount, which is this blue threshold line that we discussed. And so that y-axis is a correlation measure that's always between -1 and 1.
Perfect. We also have some questions about local resolution estimation. I'm not sure if this is the best time or later on would be a better time.
Let me get to the discussion of the plots in 3D refinement, and then we can start the next processing and come back to those questions, if that makes sense.
Perfect. The other sort of subset of questions relates to interpreting FSC curves and what the different curves mean, and which one to report as your final resolution. So perhaps we can cover that in detail later.
Yeah, I will do that. Okay. Sorry, so I'm just going to zoom forward back to where we were and switch back to CryoSpark. Oops. Okay, so right now in our hemagglutinin processing that we were doing, hopefully for most practical participants, the motion correction and CTF estimation is finished. We're not going to continue there right now. We're actually going to go back to our T20S example from yesterday, and we're going to look at the 3D refinement that you did that should have gotten to around 2.9 angstroms. And I'm going to use that to indicate what all of the different plots in a refinement mean, the diagnostics, how you should interpret the results, and what to look out for. Generally speaking, though, is like a kind of high level sort of notion about cryo-EM single particle processing. These steps that we're talking about right now are, compared to everything else, very, very well baked and very well polished. So there generally isn't a lot that you need to know about a refinement other than the final statistics that come out of it and the final 3D map. Years ago, it was the case that there were a lot of little details to watch out for, a lot of gotchas, a lot of things that weren't automated, a lot of parameters that you needed to tune, or you would get a totally wrong result or a suboptimal result. That's no longer the case. Generally speaking, we don't suggest people to really, I mean, you can always play around with things, but you will get probably very close to the best results just with the default parameters, just without really knowing what all the plots mean. I'm not saying that everyone should do that, but in case you want to go forward in your project without understanding everything in detail. So starting at the beginning of our 3D refinement job, I'm looking at, so I just opened up the inspection page of our refinement job here. And I can see the stream log view where there are a bunch of plots, various things that we're going to look at in a moment, and outputs on the right-hand side that we're used to seeing. In this page, we're looking at this stream log of images and text that comes out of our jobs. And at the top, there's a filter bar that helps us to filter through the log so that we can tell what, or we can decide which part of the log we want to see. If you click the Show from Top button, you'll see the log of the job from the beginning. That log starts off with some information about the job, its launching status, which GPU resources are allocated to it. And then we start to see, after this line of stars, logs from the actual job that's doing some processing. The first thing that the refinement job does is load up a particle stack, and it tells us how many particles it's going to be processing. So in this case, we have 9,163 particles. And in CryoSpark, you won't see this in your instance, but if you're processing at home, sorry, you won't see this on the Slack instances because we've turned off SSD caching. But if you're processing this at home or on any other system, most probably SSD caching is enabled, which means that the first thing the job will do is check to see if the particles that it needs are already available on the SSD cache of the node where it's running. If they are available, it'll skip this step and continue forward. If they're not, it'll transfer them from wherever they're hosted in your project directory to the local scratch space in your compute node. And that's for computational purposes and is a very important performance aspect, which we'll cover a little bit later today. So once the SSD caching is done, the particles are split into their two independent halves. So the refinement job in CryoSpark is implementing the full gold standard refinement. It's actually doing 2 refinements at the same time of 2 random subsets of the data and comparing those along the way, regularizing them, and then resolving a final reconstruction from which we can get a validated and trustable resolution estimate all in one shot. There are a bunch more information about what the job is going to do, the size of the particles, the size of the volume, the symmetry parameters that you've set, and so on, just to help you make sure that you've done what you expected to do. and we'll come back to masking. The next thing that the job does is load up the initial model that you provided and filter that to a low resolution. By default, if we look at our parameters, the default parameter for initial low pass resolution is 30 angstroms. So whatever initial model we provide, all information beyond 30 angstroms is going to be stripped out. That's an important thing to remember, and we need that to be the case, since for our refinement to be trustable at the end of the day, we don't want the two different half sets, which are using the same initial model, to have access to high resolution information that they could then have in common that didn't actually come from the data. So the initial model has to be filtered to a resolution substantially lower than the resolution we're going to get at the end of the day. And by default, it's 30 angstroms. We'll talk about an advanced case where you need to change that. The initial model is loaded, and for symmetric structures, we have to make sure that the initial model is aligned with the XYZ symmetry axes. Otherwise, when we try to use symmetry, if the model is tilted or somehow otherwise skewed, the symmetry will be totally wrong. So we need to estimate the symmetry axis and the symmetry position and align the initial volume to that symmetry axis. And that's what the first step of this refinement job does, in this case, because it was a symmetric refinement. If it wasn't symmetric, that's obviously skipped. So that initial model is shown here. And the plots that we see here are in general, when you see this Z, Y, and X, these are 3 orthogonal axis aligned slices through the 3D density structure. They're not projections, they're slices. So we're looking at the 3D density cutting through the middle of the protein in 2 opposite directions, and then cutting through the middle of the protein horizontally. That's the last one. And the next 3 plots are the same information, but in Fourier space. So now we're looking at the Fourier space version of the structure, cutting through the 3 different planes. And you can see here that in Fourier space right now, the structure only occupies information at very low resolutions, close to the center. As the resolution increases and we see more detail, we'll be talking about Fourier components that are farther away from the origin. Okay, once the initial model is loaded, we start actual iterations of refinement. Each iteration does the whole processing on the GPU. That's alignment of the particles, reconstruction from the particle images, estimation, correction for CTF, all that stuff is done under the hood. And there really aren't any details exposed here. And then at the end of each iteration of refinement, we start computing Fourier shell correlation curves. And then there are a bunch of plots that are made. These plots are useful to look at from iteration to iteration, but generally speaking, in real life, you probably want to look at the final version of these plots at the last iteration of refinement. I'll just go through what the plots mean so that everyone is aware, but I'm actually going to skip forward a couple of iterations so that the information is more interesting. Okay, so this is now iteration number 2. In CryoSpark, all indexing starts with 0 for historical reasons. So iteration 0, iteration 0 is the first iteration, iteration 2 is the third iteration. After the third iteration, this is now the structure we're looking at in real space. You can see that it has lots of high resolution fine detail, and this is exactly what you should expect a slice through a protein structure to look like. Lots of little high density blobs and spacing between them, which are actually slices through like alpha helices and stuff like that. In Fourier space now, we can see that our structure has lots more information going very far out in Fourier space. The edge of the box here is the Nyquist rate. So we can't see or resolve information beyond this resolution, which is twice the pixel size. So the pixel size is 1.5, Nyquist rate is 3 angstroms. In this case, I don't recall what the pixel size is. You can also see that in the slice that goes through the horizontal plane, the structure is symmetric since we have D7 symmetry enforced. And the Fourier space structure is also obviously symmetric. So that's just for intuitive understanding. The third set of plots we see here are the mask that is currently being used for this refinement. And this is an important point. There are 2 kinds of masks that get used during refinement. One of them we already talked about, which was the mask that's used to exclude solvent when we're computing the Fourier shell correlation curve. That's an important mask. The second mask is the mask that is used to remove solvent when we're aligning the particles. And those can sometimes be different masks. In a standard, with the default parameters, they're more or less the same. If you supply a mask of your own as input to a refinement job, let's say you want to mask out a particular part of the structure, then the FSC mask and the refinement mask may be different. In CryoSpark, the masking is done using something that we call dynamic masking, which is a relatively just fancy name for a straightforward thing, which is that from each iteration, we actually automatically compute the mask based on the 3D structure. So we don't ask you to provide a mask as input. That's kind of just tedious and annoying to do, when in most cases it's not necessary. What happens is that from the beginning of the refinement, if I just scroll up, at the beginning, at the first iteration, you can see that the mask is nothing. So we're not using any mask in the first iteration. Once the resolution of our structure gets to a certain point, then we start to generate a mask using the currently resolved 3D structure. So that mask is going to be slightly changing from iteration to iteration as we resolve more information. But the mask is very loose. As you can see, it's soft and dilated. So it's not cutting into the structure and it's not creating any masking edge artifacts, which unfortunately we don't have time to get into right now. It's just suffice it to say that in general, masks that you apply in real space should be soft and smooth and not too tight around the protein. So that mask is being dynamically generated. And coming back to the iteration where we were, the next plot that we see is the current gold standard Fourier shell resolution estimate at the current iteration based on the structure we've resolved so far. And we get all 4 of these curves that I mentioned before. So the blue line is computed between the 2 half maps, where here you can see the average of the 2 half maps in this plot, but under the hood there are 2 independent half maps. The blue line is the FSC resolution between those without masking. The remaining lines are with tighter and tighter masking until the light blue line, which is the tightest mask, that is going to be just like the one that we see above here. So it's called tight, but it's really very loose. The loose mask is a very loose version of this dynamically shaped mask. So we can see that right now our resolution estimate is around 3.2 angstroms, and that's where the tight mask curve drops below the 1.43 threshold. The other plots that we see, one of them is called a Guinier plot. It is a plot that's helpful for measuring the sort of decay in signal as we look at higher resolution information in the 3D structure. The reason that's important is that due to various effects like residual motion that we weren't able to correct, slight errors in CTF estimation, the actual detector quantum efficiency of the cameras that we use, any various other thermal motion of the atoms and so on at very high resolutions. All of those factors lead to a slight blurring of the 3D structure after we infer it. So the structure that we actually resolve here from the image data directly has been slightly blurred out because of all these extra factors. And we can estimate how much blurring there is using what's called a Guinier plot. And the way that this was developed was by looking at the mathematical statistics of what should a protein structure look like in terms of how much information it has at different resolutions if it was perfectly intact, so not blurred. The simple version of the story is that its power spectrum should be flat beyond a certain resolution, like 10 angstroms. And so when we measure the power spectrum, this dashed green line, and we fit this blue line to it, a linear fit to all the resolutions beyond 10 angstroms, the slope of that line tells us how much blurring there is relative to what the protein structure should look like without any blurring. That helps us to figure out how much we should sharpen the structure. And sharpening is something that we won't go into detail, but it's a simple undoing of the blurring that we've estimated here. And by doing sharpening, we can often dramatically improve the visual quality of the 3D map. The actual structural information is always present in the 3D map that we resolve up to whatever resolution the FSC plot tells us. But when we're actually displaying that 3D map in Chimera or Coot or Phoenix or what have you, if the map has been blurred, the high resolution information is still there, it's just decayed. And when we look at it, we can't see high resolution details even though they're present. So sharpening is just a visual strategy. It doesn't change anything about the data processing or the quality of the map or the resolution of the structure or the integrity of the structure. It's just a visualization tool that helps us to recover the visual ability to see high resolution details in the map. So in CryoSpark, we do this automatically as a first cut in refinement. We estimate this B factor from the Guinier plot that tells us approximately how much to sharpen the structure, and then the structure is always sharpened at each iteration by this B factor. So that when you download the map, it's already pre-sharpened and you can pretty much just start interpreting it. However, we always recommend that after you do your last best refinement, you go ahead and do sharpening again yourself using the sharpening tools that are a separate job in CryoSpark so that you can try different sharpening levels and help make sure that for visual quality, the map is the best that it could be. The next plot is a noise model estimate. And this is something that we really don't need to get into, but it's trying to explain, it's showing us what our refinement strategy has captured in terms of its estimate of how much noise there is at different resolutions in this data. And different data, depending on how it was collected, the sensor type, the motion correction, whatnot, will have different noise profiles. They generally are not really useful in terms of interpretation of any useful kind. The next plot here is the viewing direction distribution. And this data set is very small, only 10,000 images. So there are lots of viewing directions where we have absolutely no images at all, and some, like these blue squares, where we have just one image, and then an equatorial band. Here it's perfectly aligned with the azimuth rotation, so around the equator. So those are all the side views of our protein, exactly what we expected to have. And then we have another band here, which are actually all the top views. If you think of all these positions in terms of the viewing sphere, they're all near the South Pole, all like nearby to the South Pole with different azimuth values, but an elevation of close to 90 degrees from the bottom. So, I mean, in this case, because the structure is symmetric, top views and bottom views are actually the same. So it's just a coincidence that they're all at the bottom. But what this is telling us is that we have a very bimodal viewing distribution, a lot of side views, and some of them are from slightly different elevation angles. Like we have a little bit of spread there. So we have some slightly tilted versions of the side view and lots of top or bottom views. So that is actually more than enough to recover our 3D structure, as I explained before, even though we have lots of missing views, and get to a high resolution. The next plot here is another version of this viewing direction distribution plot, showing the same information in a different way. Some people find it easier and some people find it much harder to interpret. I'm going to try to explain it, but if it doesn't make any sense, then sorry, but don't worry about it too much. What this plot is showing is the level of precision to which we can recover information in Fourier space in terms of a orientation globe. So if you think of the 3D Fourier space structure that we've been looking at here, this guy, if you think of a shell at the outside of this orange sphere, every point in that shell is some Fourier component, and each one of those has been touched by whatever images have their orientation plane going through that point. So for example, in our case of the 20th proteasome, the north and south pole points have been touched by pretty much every side view image, since they all go through the north and south pole. Other points on that sphere haven't been touched as much because only certain side views or certain top views will connect with a certain point. What this plot is trying to show us is that notion. So it's an unwrapped globe projection of how many times have we seen every Fourier component at that surface of the resolution that we've considered so far. So again, for those for whom it makes sense, hopefully it does make sense, that we have this line at the top of red and the line at the bottom of red are the north and south pole. And those have lots and lots of sampling. We have lots of precision there because we have lots of measurements. These numbers are approximately equal to the number of measurements. So we have like 4,000 images contributing information to top and bottom Fourier components. And then as we move away from the north and south poles, we have fewer and fewer images helping us out. And at some point we might be getting down to like less than a couple hundred images for some Fourier components. We also have a slight increase for the horizontal plane of Fourier components, since those are touched by all the top and bottom views. So what this plot is showing us is that there's a big variance in how much information we have about different Fourier components in 3D. What we really want is for this plot to be uniform. That would be the absolute best case, but it can be very far from uniform and still give us very good results. What we don't want to have is big regions of this plot where we have 0 or close to 0 observations. That's really what missing views means, that there are parts of Fourier space where we just don't have any information. That's what we want to not see in this plot. So hopefully that makes sense to everyone. Now, as we go on, each iteration shows those same diagnostic plots. The resolution keeps increasing as we keep aligning and averaging the images better and better each time. And within a few iterations, the resolution starts to top out around 2.9 angstroms. And as we see that iteration, the iteration can also fluctuate slightly because the alignments of the images and the reconstruction change slightly here and there, and the FSC curve will move slightly above or below this threshold. The exact numerical value of the FSC in real life really doesn't matter that much. It's kind of a sort of regime type of thing that in 3.1 to 3.2 angstroms, you're going to see this kind of information. At 2.5 to 2.7 angstroms, you're going to see this kind of information, and so on. So really, what you're interested in as a biologist or practitioner is the quality of the map at the end of the day, not this numerical value, but it's a reasonable proxy to tell you how good your structure is going to end up being. In the very last iteration, there are two FSC curves, and this is the last more important point about 3D refinement that we have to talk about. And this corresponds to a procedure that we call auto tightening of the mask that are used for FSC. What used to be the case, and is still the case if you use other sort of command line programs and other tools, is that when you're doing your refinement at the last iteration, you have to create the mask that is used for FSC. It's not automatically created. And you get to choose how tight or loose that mask is. And so naturally, practitioners always will choose the tightest mask they can, where the tight and corrected curves are still close by to each other. So we know that the mask isn't problematic in that it's too tight, but it's also as tight as possible so that we can get the highest resolution estimate that is possible for this reconstruction. And this is a totally valid thing to do, since we know that the FSC resolution depends so heavily on the mask. We want to choose the mask that excludes the most solvent, since we really don't think of the solvent as being something where we have resolution, and we want to just look at the protein. So the tightest possible mask that doesn't create any correlations or edge artifacts or anything like that is the best mask. So that used to be a process that everyone had to do by hand before you prepare your images for publication and so on. You would go and fiddle with the mask tightness until you get something that looks like this. We've just taken that procedure and made it automatic in CryoSpark. So in the last iteration of a refinement, your FSC mask is automatically tightened to the point where it doesn't introduce any artifacts, but it creates the resolution estimate that you can trust and use as your final values. You can also download these plots, and you can also download the actual FSC curves and everything else that you need from these buttons. And you can also download, if we scroll back up to the top of the job, you can also click on the download button in the volume section and download various outputs from the refinement job. So you can get the original map, which is the unsharpened reconstruction. That's useful for some things, but generally not for visualization purposes. You can also get the sharpened map, which is the map that's been sharpened by the automatically estimated B factor. You can get the independent half map reconstructions in case you want to do your resolution estimation or something else in another program. You can download the mask that was used for refinement in the last iteration. You can download the FSC mask and the auto-tightened FSC mask. You can also download a version of that precision plot, but I don't think many people use that. So that's everything about a refinement job. At the end of the day, to answer one of the questions that someone had, the final resolution you should report is, right, in the last iteration, the second FSC curve where it says after FSC mask auto tightening, that is the final resolution that you should report. And that's fully validatable, and you can download the text version of that as well if you want to make the plots in another program. These curves and everything are available in sort of a tab separated value tabular format. So you can download those as well, or you can download PDF or PNG versions of these images and throw them straight in your publications. Okay, I think that's everything I want to say about refinement. The next thing I think I'm going to just quickly go over is the HA trimer dataset that we were previously working on. So in this HA trimer dataset, now for people who are part of the practical, what you want to do is create a exposure curation job and connect the outputs of your patch CTF estimation exposures to that job and then queue it. And I'm just going to jump over here to my instance where I've already done that. When the job starts off, you'll see its log, and then the interactive tab will show up. So if you click on the interactive tab, you'll be presented with this interactive version of the job where we can start to look at the data and curate its quality so that we can pick images that we want to keep. So I'll just give a minute for practical students to get to that point. I can answer a question or two if there's something worthwhile right now.
Yeah, sure. We had a few regarding refinement and specifically masking. So first of all, is the auto tightening done for all data sets?
Yes, the auto tightening is always done at the end of a refinement. For very, very low resolution refinements, it really won't make any difference. But for high resolution structures, it can mean a 0.1 or 2 angstrom difference in the final numerical value. And like I said, you should always use the auto tighten mask, since the masks that we used previous to that are very liberal. And if you were doing it manually, you would always use the tighter mask. So you should.
Is there any parameter or any way to know that the final tightening of the mask is correct?
Yes, and that's something that everyone should be very much aware of, which is what I mentioned as the noise substitution correction procedure. And this is something that is a very widely used popular technique. It's from a paper by Richard Henderson and others who developed this noise substitution method that allows us to detect whether or not the mask is too tight. And as long as the purple line, the corrected curve, and the blue line are close to each other, and the final resolution that we report is always the corrected version anyway, the corrected curve tries to discover the presence of any aberrations or correlations produced by the mask. So if the mask is somehow incorrect in the sense that it's too tight or it's too sharp or it's too whatever and cutting into the protein density, that will show up directly here as a discrepancy between the tight and corrected curves. So as long as they're close together and you end up with a numeric value that's similar or same, the corrected curve and FSC resolution that you get there is what you can trust. There's one other thing, a question that comes up on the discussion forum from time to time, that often you'll see a sharp drop in the FSC right at the place where the tight and corrected curves diverge. This is actually part of the expected behavior for the correction protocol. What you're actually interested in is the high resolution end of the corrected curve. I'm going to try and find a structure where that's the case. Let me see. Maybe in this non-uniform refinement. Yeah. So here is a resolution estimate from this non-uniform refinement. And you can see that the corrected curve, the purple line, has a sharp drop at a certain resolution, 7.7 angstroms here. And then it comes back up to meet the tight curve. This drop is part of the expected behavior of how the correction technique works, and it really all depends on where the noise substitution correction is started from. If we had started over here, we wouldn't see the drop, but it's really irrelevant. What you're interested in is that the two lines are very close together or coincident at the high resolution end where you're actually measuring the resolution. If that's the case, then you know that the mask is correct and you can go forward. And generally speaking, it always will be, since the auto tightening only produces masks that are correct in that sense. Like we literally measure for a bunch of different masks the tight versus corrected curves, and then pick the mask that gives the best resolution but no discrepancy between the corrected and tight curves. So it's something you really don't have to worry about very much, but it's important to know.
One more point on interpreting the FSC curves is that quote unquote huge bump that we see in the FSC normal, and how would we interpret it?
The huge bump, I'm guessing the questioner is asking about the particular one we're looking at right now. That's a great question. I was going to come to that a little later when we actually process this data set. But the bump is related to the fact that this is a membrane protein, and it's a very common phenomenon that you will see in a lot of membrane proteins. The reason for it is that the micelle, the detergent micelle or lipid nanodisk that may be around your protein, is a highly disordered but large amount of electron density mass in your protein structure. And it causes there to be a systematic loss in correlation between the two independent half sets, because the micelle itself is just so disordered that in every particle image, it's different. But it has a substantial amount of power, much more than the background noise, at intermediate resolutions, like between around 8 and 5-ish angstroms. The micelle is the dominant source of signal in the images. Beyond that, the protein density shines much brighter because it's coherently the same from image to image. The protein is rigid, whereas the micelle is disordered. But in that window, the micelle, we should actually most of the time expect to see this bump, since the micelle is creating a loss in correlation between the two half maps. That doesn't mean we can't trust the structure anymore. It just means that for membrane proteins, this is a common phenomenon that we would expect to see. Still, at the end of the day, what we're concerned with is the resolution at which the FSC falls below the threshold that we have come to agree on as the place where we can no longer trust the structure. Any time is above that is a good thing.
Thank you. one more kind of general question to sum up questions about user preferences in this domain. So can the user still manually adjust mask tightening after the final iteration and refinement? That's the first part. And the second part is more generally, when would we supply our own mask versus using the dynamically generated mask?
Great questions. Three answers. The first answer is that for both types of masks used in a refinement, the parameters of that masking in terms of the tightness can always be adjusted. What you need to do is, if you want to adjust the mask that's used during refinement, then in the parameters of your refinement job, you will find a section called, or a bunch of parameters related to the masking, which are, sorry, this is the wrong job. You will find a bunch of parameters called dynamic mask X, Y, or Z. And the dynamic mask parameters control how the dynamic mask is generated from iteration to iteration. So there's a threshold that determines how we clip the 3D structure at the current iteration to figure out which parts are protein, which parts are solvent, how far we dilate that initial mask in angstroms, and then how far from that is the padding of the soft fall off of the mask. So by default, we dilate by 6 angstroms. So that's quite far away from the protein. And the mask continues for another 14 angstroms or out to 14 angstroms in a soft fall off down to a value of 0. There's also a parameter that controls when we start doing dynamic masking. Only if the resolution exceeds 12 angstroms, then we start doing dynamic masking. And so you can change any of those parameters. You can also provide as an input to a refinement job. If I clone this job, you'll see that there's a mask input, and there you can connect any mask from any other source, for example, having imported it or a different job that generates masks, and use that mask during refinement. For the FSC part, you can also do that by creating a job called FSC validation. And this implements exactly the same procedures what we compute FSCs in a refinement. It's just a standalone job version of that. You can provide a volume connection, and that connection, if we expand what it's connecting, is actually connecting the 2 independent half maps. So that's what we're using for doing the FSC validation, as explained. And then you can provide your own mask of any kind. Or you can ask the job to generate a new FSC mask where you use the same dynamic masking type of parameters to generate that mask. And then you can, that will create the final FSC curves exactly the same way as a refinement job. And you can use those any which way you'd like.
Perfect. And I think just to sort of sum up the conceptual notion of this entire section that we've been discussing. So overall, the goal, and you can kind of just fill in the blank / elaborate on this. The goal we are trying to get the tightest mask at the last iteration of refinement, because at that point we get less noise from the solvent, which is usually not contributing to the resolution estimation, or rather the resolution estimation that we care about.
Precisely correct. Yeah, the purpose of masking is entirely, there are 2 reasons. One is regularization during refinement. We don't want noise that's building up in the solvent areas to affect the alignment of particles, so we mask those out. And for resolution estimation, we don't want to care about the solvent when we're trying to estimate the resolution of the protein. Since you can think of a conceptual experiment where you take a protein in a small box that has noise in the solvent and measure its resolution. What you'll end up with, if you don't do any masking, is an average resolution between the areas where there's no structure, which is basically a resolution of nothing, and the protein resolution. You'll get an average of those. And then you can think of the exact same protein structure, the same map quality, same everything, in a big box with a lot of background, a lot of solvent. Now the resolution estimate without masking is going to be, again, an average of everything, but there's just so much more volume in the solvent compared to the protein that it totally diminishes the resolution that you think you see, because now you're looking at this huge empty box with just a tiny protein. But really the map quality is identical. So masking is the only way where we can get rid of that, produce the invariance to solvent that we would like to have during resolution estimation.
Perfect, thanks. We do have still a number of questions, but as I mentioned, for the sake of time, and also because we do have a morning session tomorrow with some of the other panelists on resolution estimation validation, we'll defer some of those questions to tomorrow as well.
Perfect. I think that makes a lot of sense. So what I'm going to do then is head back to our hemagglutinin trimer dataset, where everyone should have created a curate exposures job by now. And now on this job, I'm going to make it full screen. We can look at the whole interface, and now we have, compared to yesterday, a few more movies to play around with. And I've particularly chosen this set of images from the HA trimer dataset so that we can actually see something useful out of them. So first of all, again, explaining the interface. On the left-hand side, there is a scrollable table of all the images in our dataset. So this could be thousands if we had a big dataset. You can click on any of the headings to sort by that particular parameter. And then on the right-hand side in the overview page, we have a 2D scatter plot. You can also turn that into a histogram if you want, but generally scatter plot is a little bit easier to interpret. And we can choose what the X and Y axes are actually representing in terms of which parameter we're plotting or which statistic. So by default, we're looking at on the X axis is index. So that's just the order of the images as they were imported or as they were collected. And the Y axis can be something that whatever we want. Average intensity, average defocus, astigmatism, phase shift, etc. What I'm going to do is first plot what I recommended yesterday as probably one of the more useful statistics to measure, which is CTF fit resolution. So I'm plotting that over time here. And you can see that as this data session collection was in progress, I can zoom in a little bit to just this part. Maybe zoom out a little bit. As this data collection session was in progress, the CTF fit resolution was kind of hovering around 4.2-ish angstroms, and then suddenly dropped to a more average of 3.2, 3.1. So we can see that there's kind of some difference between the movies that were collected earlier and later. And that's actually what we want to hone in on. If we plot a different parameter, now let's look at something like relative ice thickness, which we've already discussed in detail today about how it's computed, then we can see even more clearly that at the beginning, we were looking at images that had an ice thickness, relative ice thickness around 1.15. So that meant that the ice band had 15% more power than the rest of the background. And then we started seeing images all of a sudden that had an ice thickness of only 5%, ice band power of only 5% more. So relative ice thickness of 1.05. So what we can see here clearly now is that probably these early images were collected in an area of a grid or square or something that was not very good. The ice was too thick. And later on, we started to get better images. So we want to hone in on that a little more. What we can do is actually plot both of these parameters together and see if there's a correlation between them. So let's see CTF fit resolution versus relative ice thickness. And zooming in on this a little bit. Now we see that there's clearly two sort of clusters. There's a bunch of really good images that have on the x-axis, what we're looking for is a lower, so more left CTF fit. Let me just zoom in again a little more here. Yeah, so this bunch, which have a better CTF fit around 3.2 angstroms. And then this bunch, which have a poorer CTF fit around 4 angstroms and also a worse ice thickness. So we can clearly tell that ice thickness and CTF fit in this case are highly correlated. And so our conclusion is that the reason that our CTF fit may not be great is because the ice is thicker in some cases and thinner in some cases. In a case like this, when you're doing data curation, it's important to think about your end goal and the context of your overall data set and what you're trying to achieve. If you've collected, let's say, 10,000 images and all of them have thick ice and all of them have not great CTF fits, then you shouldn't throw those away because you can still get a 3D reconstruction. It may not be the highest resolution anyone's ever seen, but you can still make good progress with that data set. On the other hand, if you have a data set of 10,000 images and 2,000 of them appear to be pristine, very thin ice, perfect CTF fits, very little motion, and the other 8,000 are worse, much worse, you're actually probably better off throwing away the 8,000 and only focusing on the really good 2,000. An important fact about cryo-EM data processing is that high quality images are worth a lot more than a lot of low quality images. So whenever you have the chance to pick better data, as long as there's still enough of it, it's not just one micrograph that was really good. As long as there's enough of it, you should probably opt for only continuing with the best data. You won't gain that much by adding more low quality particles to otherwise good particles. Like I said, the opposite is also something to consider. If you only have medium quality data, you should use as much of it as you can, since more particles do create better reconstructions if they're all of the same quality. So that's kind of what we want to think about. So in this case, now we know that we want to really keep only these images which have a low ice thickness and a great CTF fit. But let's just dig in a little more to see what's the difference between these. Can we visually tell something about the images and get some idea of what was happening in our sample data collection? So what I'm going to do is sort the table by relative ice thickness. At the beginning, we have images that have very thin ice. So I'm going to click on one of them and see what it looks like. Maybe it's not a great example. Pick another one. Okay, so this is an image that has lots of particles. And in the Fourier transform, we see there's no ice band. And in terms of a CTF fit, although in 2D, we kind of stop seeing the tone rings after a little while, when they're averaged in elliptic averaging or circular averaging, we actually see that the tone rings go out quite far in resolution all the way to 3.4 angstroms. So that's pretty good. Let's look at another case where we have a better CTF fit and a low ice thickness like this one. Here now, this is again an image with lots of particles, relatively little ice band. We see that there's a different kind of sort of ice issue in there, but maybe that's not too important for us. And our CTF tone rings go out pretty far as well to 3.2 angstroms. We can also see that the motion trajectory that we had for this data set, if we look at the rigid motion, sorry, I'll just let you see this in the zoomed in view here. If we look at the rigid motion trajectory, there's a huge amount of motion. The sample starts here. Because it was tilted data, like I said before, there's often a lot more motion due to the doming and other aspects. The sample starts here and moves in the first couple dozen frames almost 35 pixels, which at this pixel size, which is 1.3, is something like 40, 45 angstroms. So that's a lot of motion. That's almost like probably half the size of the particle. And that means that without motion correction, we would not get anything out of this data. But our motion correction has faithfully resolved this huge amount of early motion, and then things kind of stabilize. But locally, the ice is deforming in a pretty interesting way. Sorry, I'll zoom out here again. Now we can see that in this case, some parts of the ice are moving. I mean, they're all kind of moving away from the center. The very center of the image is not moving too much. These plots, by the way, are only showing the relative sample deformation. So the overall full frame motion has been subtracted out. So we can just see the difference between different parts of the image. And there's also some kind of sort of slight rotation type of effect going on where patches in this corner are moving kind of sideways and other patches moving in the opposite direction. So that's interesting to see as well. Now, on the other end of the spectrum, if we look at images that have a very large ice thickness and worse CTF fits, we can maybe start to see that there's something interesting in the data. Here's a good example. So now this is an image that has plenty of background power in the ice band, and it has some really sharp signal content at particular orientations in that same band of ice power. And that actually, for people who are familiar with crystallography, which probably everyone is, actually corresponds to the electron diffraction from ice crystals. In this image, we can see, first of all, the ice is thick. You can't see that by eye, but we know that the ice is thicker. But here you start to see some interesting aberrations that are kind of like a dark splotch with a little bit of a halo. And after looking at enough data, you'll come to recognize this as crystalline ice. And that crystalline ice is actually like crystalline in the sense that it's all ordered water molecules, and they diffract electrons in 6 directions, I think, creating these bright spots in the ice band. So that's actually exactly what shows us that this ice was thick enough. First of all, it was thick, and it also has crystalline ice growing on top, which is something that we don't want. So these kind of images we potentially want to get rid of. Another example here, maybe we'll see something more interesting. This one is just very thick ice, lots of power in the background. There's one that I'm going to keep clicking until I find where we can see a nice shearing of the ice. Okay, so these are all relatively thick ice. Let me try one more. Oh, we saw that one already. Here's another example. Here's a good example. So this is the one I wanted to show. This is another case with very thick ice and lots of crystalline ice formation that is causing not only individual bright spots of electron diffraction, but also these streaks where we have a crystal where its lattice is kind of rotating. So we get diffraction in a streak. At least that's what I presume that it is. So these are exactly the kind of images that we want to get rid of. You can see in this 1D plot that like in the ice band here, there's so much extra CTF power, or so much extra oscillations due to the high bright points in that ring of water. Anyway, so that's what we wanted to detect, that we wanted to make sure that we really want to throw away all these images and we want to keep all these good ones. So what we're going to pick down here in our sliders is to choose one of our parameters. Let's say it's CTF fit resolution. We're going to take only images that have a CTF fit better than 5 angstroms. So that cuts out all these weird outliers out here. And we're also going to choose that we only want relative ice thickness up to maybe 8%, 7-8%. And that's going to cut out all of these thick ice images. And now we're left, in terms of the blue dots that are selected, only those that have good CTF fit and thin ice that we were looking for. If we look at the table, it's also colored in the same way as the dots. So everything with small relative ice is selected and everything else is gray. The job for actually doing curation of the data, this is not enough. You have to click one more button to actually form the selection into an accepted set of particles. The selection is something that's kind of just a temporary selection based on the sliders you've picked right now. To finalize that selection, you have to click the checkbox to accept your selection. You can also choose to reject your selection, which will reject the images that you've selected. But when you click the accept selection button, it should just reload this page. Done something wrong. Sorry. Yeah, sorry. So when you come back to the data, I'm just going to make this plot into the same thing that we had before. Now, when you click the select button, accept selection, all of those rows that we had selected turn green. And that means in the final output of this job, those micrographs will appear in the accepted output. Everything else will be either uncategorized or rejected. The reason we've done it like this is so that if you want to do multiple queries or sort of intersecting sets, you can repeatedly create selections with different slider choices and then accept or reject the selections to overlay their queries into whatever form you want. I don't know if a lot of people use that advanced functionality, but it is possible. You can also choose to accept or reject manually individual exposures, although I highly recommend that most people don't do that. So this is what we wanted to see, and we've now gotten exactly what we want. All of the good images are accepted. So now we can go ahead and click done. Oh, sorry, I'm gonna minimize this again, click done. And that's gonna ask us if we wanna save the outputs and end the job, say yes. And now our job is finished. And we can see that our accepted exposures are only 58 and our uncategorized exposures, which are the ones that we didn't wanna select, are 42. So if we were going to continue processing, we could take these 58 and continue and use only those for downstream processing. And in fact, that's exactly what we have done when we process this data set ourselves to get to 3 angstroms. We just ignored all the bad images. That was more than half of the 600 movies that were collected. We only took the best ones, and that got us to a state-of-the-art resolution on this data set. Okay, I think that's everything I wanted to say about exposure curation.
That actually brings us perfectly to a scheduled break.
Great.
So perhaps we can all take 10 minutes and be back at
Looks like 10:45, 10:44, 10:45. How about 10:45?
10:45.
Okay, I'll
Joanne, just great. There we go. All right. I'm going to start sharing my screen again. I believe what we're going to start with is more questions. To begin, can everyone see the right screen here? My questions page?
Yes.
That is correct.
Great.
Perfect. So some questions on exposure curation or manually curate exposures, as it's also known in CryoSpark. Do we trust images that have a negative average intensity?
In general, yes, they're probably fine. A negative average intensity? Actually, I'm not too sure why an average intensity would be negative. Maybe we can come back to the question. I'm not too familiar with what the average intensity value should be. I think we recently added that field to
yeah. Actually, I think it's as long as there's not a number that's too far off the relative average, that's when you should sort of be wary about the actual value. But in general, the negative number should be fine.
Great.
Okay,
Thanks.
hopefully that clarifies. Thanks. Just a recap of how do we measure ice thickness in CryoSpark?
Sure. So I can just go over that again in actual CryoSpark here. So as I was saying in the, let me just build this job and create it again. during Hatch CTF, what we do is we measure the amount of relative background strength in the image in Fourier space in the shell of frequencies or band of frequencies that correspond to ice, water and ice. And we can see that most easily by actually looking at an image and looking at its Fourier transform. So this is the raw micrograph. This is the Fourier transform. And you can see that if you look at the background noise out here, it's kind of dark gray. And in this band right here, which if I had axis labels would be around 3.5, 3.7 angstroms, there is excess background noise, background strength in the image, this white band. As I was explaining earlier, this white band corresponds to signal deposited in the image from water molecules in the ice, either because of multiple scattering events or because of the fact that from frame to frame during motion correction, the ice doesn't line up with each other. And for various reasons, those water molecules are not forming a coherent signal in the image, which is why they don't contribute to the tone rings, but they are forming background noise in this particular frequency band. The reason they're in this frequency band is that water molecules are always a certain distance apart on average. If it was crystalline ice, then the water molecules would be exactly a particular distance apart and exactly in a particular orientation, which is why we would see in some cases those bright spots in the Fourier transform, which are the electron diffraction pattern of the ice crystal. When it's not crystalline ice and it's amorphous, there's this extra band of power in the background. And this is not something that is new. This sort of idea of measuring ice thickness in this way has been developed by other teams and other people who worked with cryo-EM data processing in the past. And it's something that we've adopted as well as a technique for getting an estimate of the relative ice thickness of an image. And it's not infallible, and it's not an absolute measure of ice thickness. It's just relative. It tells us across this data set which images have more or less thick ice. And that's as much as we can use it for. But it turns out to be quite handy in practice. One thing I just wanted to show everyone was the actual processing of this hemagglutinin data set. When we originally did it was done in CryoSpark Live, which is what I'm showing you here, just so you know what it looks like. In CryoSpark Live, we can easily scroll through all the images in our data set and pick out ones that are either good or bad. So I can, for example, go over to the CTF fit plot and see across my data set of 600 movies. At the beginning, a lot of the images had very poor CTF fit, around 6 or 8 angstroms. And if I click on those dots, I can get to that image. So I can see at the beginning, whoever was collecting the data was collecting images that were not of great quality, not too many particles, lots of aberrations and ice crystal growth and so on. And that was sort of the case for a little while. And then they obviously moved to a different part of the grid where things got a little bit better, but still not great. CTF fits around 4 or 5 angstroms. And what we can see in our ice thickness measurement is that the ice thickness was relatively thick that whole time. And then finally, they moved over to an area all of a sudden here where the ice was much thinner and the relative ice thickness was much better. And the CTF fits are also much better. So in this region of their data collection at this time, they were in a square or grid that was really good. And when we were processing the data, we simply threw away all the data that was worse than this section of good data and only used particles from those images to get our 3 angstrom result on this data set. So I just wanted to show everyone on the whole data set, what does that look like?
Perfect, thanks. Also in regards to actually discarding images on the basis of ice thickness, let's say that a sample exhibits, or rather the protein exhibits preferred orientation, especially in thin ice. Would removing the thicker ice movies make it worse overall? And I'm assuming they mean make it worse in terms of the overall resolution of the refined structure.
Certainly that is a possibility. And that's exactly the kind of advanced scenario where you would have to process your data twice. Once to find out that, in fact, you do have preferred orientation when you pick up only the thin ice movies. And once to find a way around that problem by re-including other images or selecting a different ice thickness range that you want to keep. But definitely that's something that is plausible, that it could happen. Yeah.
Right. Also along those lines, are there any other pitfalls of actually including bad images in further processing steps? So let's say we did do exposure curation, or perhaps we didn't, but we ended up keeping some quote unquote bad images, which are bad on various statistics. Well, how will that affect downstream processing?
In a couple of ways. First, like I said, it never helps to add poor quality data to otherwise good data. So it's very hard to imagine that those poor quality images would actually help in any way. The ways that they can hurt are in a number of ways. One, if the bad images that you didn't reject, that you could have rejected at this stage, have all kinds of aberrations or characteristics that mess up some other part of processing, for example, particle picking. If there are lots of carbon edges or these kind of ice crystals or sheared ice or whatever it is, particle picking may pick up a lot of that junk. And if that's not weeded out, it will end up creating a whole bunch of bad particles that then you have to get rid of at 2D classification or 3D classification time, where those particles may impact your ability to, for example, classify small conformational changes because so much of the signal is swamped by these bad particles. Likewise, during a refinement, it is possible that if you, let's say you have a data set of 50,000 great images, and then you add 50,000 more poor images, but they're not so bad, like they're still of the actual protein, they're just from bad ice regions. It is possible that those poor images can reduce the overall resolution of the structure because they each contribute noise in high resolution domains. So that effect is not really so linear. Like it's not like if you had 50,000 good images and you had 50,000 bad images, your resolution will get cut in half. It's more subtle. So you might lose only 10% of your resolution or 5% by adding twice as many bad particles. It won't be so drastic, but they do subtract from your ability to resolve high resolution details and especially to do classification. When there's bad data present, all the classification techniques, whether it's 2D classification or 3D classification or whatnot, Ab-initio, Reconstruction, even 3D variability analysis, the difference between the good and bad particles in their high resolution details will be stronger and more detectable than the difference between conformations in some cases. So by having lots of bad data in the mix, you can make it hard for the algorithms to separate conformational changes.
Thank you. Final question regarding exposure curation and combining data sets. So in this example that we're looking at here with the HA trimer, it was collected at 40-degree tilt. What if we actually had two data sets, presumably containing the same protein or complex? One was collected at one plane and the other one was collected on a tilted plane. Yep. What's our strategy then to work with both of those data sets? Can we combine them? Can we do patch CTF estimation, refinement on both of them together?
Yes. In general, you can treat them totally exactly the same and you can fully combine them. You can even process them all as just one set. Patch CTF will detect the tilt for the ones that are tilted and not for the ones that aren't. As long as they have the same pixel size, everything else will take care of itself and you can directly refine all the particles together. Now, whether or not that actually helps or not is a question. If you do have preferred orientation and your untilted data only has certain views, but let's say, I mean, one thing about tilting the data is that the ice naturally becomes thicker simply because of the tilt. And so generally speaking, untilted data will be of higher quality just naturally, even the same exact sample, same exact grid. So if you have lots of untilted data of high quality and only some tilted data that's showing you some diverse views, in the end, you may be limited in your resolution by those diverse views that you needed, but you only have tilted data for. And so adding both together in some cases may or may not produce an actually better result, but it's definitely not difficult. You can just throw them all in together and not worry about anything. You can even curate them all at the same time. You will literally see in the curation job, if you plot actually I can show you this, index versus defocus tilt angle. The defocus tilt angle is something that I didn't mention so far, but it's estimated by patch CTF as the angle of a plane that fits through the defocus landscape that we've measured. And so we can see here that although the original practitioners intended to collect this data at 40-degree tilt, most of the images are closer to 50-degree tilt. And some where the CTF estimation was wildly wrong have very different tilt angles. But by and large, the images were around 40, 50 degrees tilt. So when you make this plot, you'll see a bunch of untilted data and a bunch of tilted data, or a mixture of them depending on what you did with the tilt.
Great, thank you. I think that concludes right now the questions that we have regarding exposure curation.
Excellent, that's great. So I'm going to switch back to the slides at this point. And what I'm going to go through next is, we're going to get to some more practical data processing in a moment, but before I get to that, I had a case study of an interesting data set that I was going to present yesterday. I brought that into the slides for today just to go through it. It's an interesting data set, membrane protein, I'll be able to talk about some of the characteristics and show you some of the images and some of the final results we're able to get. And it's more of just an example of what you can do in CryoSpark. It also uses some of the advanced algorithms that I'm going to talk about in lots of detail this afternoon, like non-uniform refinement and 3D variability. But it's just a nice case study that uses a lot of the features that we've talked about so far. So the example dataset that I'm going to be talking about is a very large dataset of 25,000 movies containing a NaV 1.7 ion channel. And this is a therapeutically relevant pain receptor. The data was originally collected at a pharmaceutical company, Genentech, and they were able to publish the structure and also deposit the data online for everyone to play with, which was great. It's available as Empire 10,261. In this data set, it's notable for a few reasons, or it's interesting. It's kind of a good representation of what with cryo-EM you can do and what a lot of people are trying to do in practice on difficult targets with flexibility and multiple conformations, ligands bound, and all kinds of things. This data set contains this NaV 1.7 channel, which is, I'm not extremely familiar with the biology, but just to a sort of coarse degree of accuracy, a four-fold symmetric, C4 symmetric membrane protein that has almost all of its mass, protein mass, inside of the micelle, inside of the membrane domain, and a 4-helix bundle that sticks out. In this case, in order to purify the protein and sort of stabilize it a little bit, the team that was purifying the data or purifying the protein also had attached 2 fabs to one side of the protein. And the channel itself, being an ion channel, generally has an open and a closed state, which coexist in the sample. And what's really nice about this data is that both states are present. In this case, the team also had bound a spider toxin, which is known to cause pain by binding to this pain receptor. That spider toxin is bound to the structure. So it's a very interesting data set overall. In the original study that was published just a few months ago last year, the people who processed the data were able to separate the 2 conformations, the active state and the deactivated state. And there's a strong conformational change between those across the entire structure. And got both of those maps to a sort of intermediate 4-ish, 4.5-ish angstrom resolution. And this is the overall map that they deposited for the structure. I'm just going to show some examples of what the data looks like, since it's a really interesting data set. It has lots of the characteristics that we've talked about. It's so large, it really needed a lot of curation. Many of the images are collected at the edges of holes because the protein, I'll just switch to the next one. The protein, hopefully you can see it here, the yellow circles are picks from our CryoSpark blob picker. The protein likes to aggregate near the edges of the hole. And that's maybe because the ice is thin in the middle, or for some other reason during sample preparation, the protein liked to be at the edges of the hole. And for that reason, and also the concentration of protein is highly variable from image to image. Some of them have lots of protein, some of them have very few. And because the proteins like to aggregate at the edges of the ice, a lot of the images have a carbon edge or whatever kind of edge this is. And they also have a strong defocus gradient because the layer of air-water interface where the proteins are probably adhering is curved at the edges of the hole where the ice is kind of concave. And so at that edge, the ice is curved. You can see that in this patch CTF plot where patch CTF is automatically able to determine that the ice is kind of curving like that towards the right-hand side of the image. And in other cases, it's more or less curved. But in all cases, there's lots of variation in the data, lots of different kinds of images, some very good quality ones, some very poor quality ones. So it took a lot of curation. This is actually an example of a data set. This is something I mentioned as a small detail yesterday, but it's this is an example of a data set where a technique like patch CTF estimation is actually very important because the protein itself is small, it has a huge disordered region, the micelle, and it's flexible. And so it's a perfect counterexample for methods that try to do post-refinement CTF refinement, so trying to find the CTF of individual particles by comparing the 3D structure that we resolved to the image data. That kind of a technique, which is also available in CryoSpark, turns out only makes things worse on this data set because the protein is so flexible, has such a large disordered region that the reference structure never matches up with any particle image. And so CTF refinement actually makes everything worse. But patch-based CTF that doesn't depend on a reference structure and just works right off the bat using the image data alone is able to get more accurate per particle CTF estimates, and that's an important point. So we were able to process this data in CryoSpark, and again, as just a case study to show what kind of thing, what processing we did and what the results were that we were able to achieve. I'm first going to explain what was done, or the original result that was published. 25,000 movies of this data set were processed, resolving. This is one of the 4 symmetric subunits. They're not quite symmetric in this structure because of the asymmetry introduced by the fabs, but one of the 4 subunits in the actual ion channel. The original team was able to resolve these structures 3.6 angstrom for the active state, and that's the structure that I'm showing here. So the red density is the deposited map from this original paper, along with the atomic model that was built into that map. You can see that in some parts, so this helix, for example, is part of the very central core region of the protein. It's relatively high resolution, lots of detail for side chains. And in other parts, like the peripheral regions, there is less detail, a clear sign of flexibility and other issues. And they were able to resolve the active state to 3.6 angstroms and the inactive state to 4.2 angstroms. We reprocessed this data in CryoSpark, the same movies starting from scratch. We used patch-based motion correction, patch-based CTF estimation, blob particle picking. So we didn't even do template picking or create templates or anything like that, just directly used blob particle picks. We got around 700,000 particle picks at the beginning, and then used 2D classification to whittle that down into about a little under 500,000 particles, and then used ab-initio reconstruction and heterogeneous refinement to resolve multiple conformations. Again, we found the same active and inactive states at that point, where we were looking for discrete conformational differences. But refining those structures, thanks to the advances in patch motion, patch CTF, and also using an algorithm that I'm going to describe a little bit later, non-uniform refinement, which is specifically designed to handle the case of structures with lots of disordered regions like membrane proteins. We were able to resolve a much higher resolution structure for both the active and inactive state. So this blue density I'm showing here now is the CryoSpark results. We haven't published this anywhere or really done too much with it yet, but I'm just going to flip back through between these. So the red map is the original density that was published. The blue one is the CryoSpark density. And you can see, if you look closely, sidechain detail in the central region is much more resolved. And in the peripheral region as well, there are lots of details that were not present before that we can now see. And in fact, some parts of the model building can be shown to be now incorrect based on the new blue density that we have. So the active state, we were able to improve from 3.6 to 3 angstroms, and the inactive state from 4.2 all the way to 3.2 angstroms. And those improvements, like I said, the processing chain that we did, we actually did the initial processing in CryoSpark Live, which implements the same patch motion, patch CTF, blob or template picking, etc. And we use just blob picking, followed by heterogeneous refinement and ab-initio reconstruction and non-uniform refinement to get these 2 density maps. So that's an interesting example. What's really interesting about this data set is the conformational heterogeneity. It actually has, as we've already seen, the open and closed states of the channel. And these are very different in their conformational configuration. In the activated state, the protein, the pore is kind of square shaped, and the helices in that region are more or less symmetric. And in the inactive state, the symmetry collapses from 4-fold symmetry to 2-fold symmetry, and the pore squishes into a rectangle that closes the space, I guess. I mean, that's my understanding of it. I don't know actually the whole biological context or story. But that is the 2 conformational states that we can determine based on standard classification methods that we've described so far. So that's like, for example, ab-initio reconstruction, heterogeneous refinement, 3D classification, etc. Those methods are all designed for and can work very well with data that has a discrete conformational change, where there are multiple discrete states that are separately present, and each one they're both very different from each other, and there are populations that are in either one state or the other, and not really too much in between. So those states are resolvable by standard methods. But when we look at the 3D density map, and for those who have looked at electron density maps before, there are clear signs of flexible blurring around the periphery of the protein. So even when we looked at these peripheral parts of the structure that are closer to the outside of the membrane region, and that's actually where the spider toxin is bound, so they're therapeutically interesting as well. Those regions are really blurred out, and the structure definition, the map quality is very poor. And we also see the same thing at the edges of the fabs, and the fabs themselves also have a lot of washed out characteristics. I'm not going to go into how you can learn to sort of interpret density maps for this kind of thing, but suffice it to say that you can see that there's clear signs of flexible deformation happening in the protein. And that's exactly why this data set is so interesting. It was one of the test cases from which we used to develop a new algorithm that was released in CryoSpark about a year ago, but we just wrote a paper about it that's on bioRxiv, and I'm going to talk about that a little bit in the afternoon as well, to actually resolve continuous flexibility without 3D classification, without separating into discrete substates, directly resolve continuous flexibility and continuous conformational change of the this same nav channel. So these two videos that I'm showing here, sorry, this one went a little fast. This one is the first type of conformational variability that we can see. And you can see in the structure, the two fabs only bind, there's only enough space for two fabs to bind to two of the opposing subunits. They could have bound to the other two, but there's only enough space for two. So there are two fabs bound. And the first type of variability that we find is that the fabs move closer and further apart, and the overall structure of the protein also bends. You can see that these peripheral helices, which are the ones that are poorest resolved in the structure, are moving by at least a couple of angstroms, 2 or 3 angstroms or more, and the fabs are moving by a huge amount. So that's one kind of motion that we can detect, flexible motion. And the second one, sorry, is an opposite kind of motion. I'm just going to play this video again. This is looking at the same view. So now the subunits that don't have fabs connected, this time the fabs aren't moving, but when we watch this video play, we see that from a side view, those two subunits now are moving up and down relative to the rest of the structure. And those peripheral helices are also highly blurred out in the refinement result that we get. So that's we're going to talk in detail about how to get these kind of results, how to resolve continuous flexibility, and lots of people have used this now for several projects, including for small proteins, GPCRs, continuous dynamics of larger things, ribosomes, etc. And it's a very exciting space, since for single particle cryo-EM, the fact that we collect individual particle images is both a blessing and a curse. A curse in the sense that we have to solve this huge computational problem to connect the images from connect the information from all the different images into a 3D structure, but a blessing because in each individual image, we actually get in aggregate a lot more information than we would, for example, from a crystal, where we're only collecting information in aggregate across the whole crystal, and we can't tell anything specific about a particular protein. With single particle EM, because we're looking at single particles, we can actually get into understanding and resolving the dynamics of the protein, which is definitely a very open and very interesting, exciting area for new development in the space. So that's all I want to say about this case study right now. And I think what we're going to do next is move over to the next data set that we want to practice in our practical, or go through in our practical. And that is a data set that we actually saw a little bit yesterday. The data set that we're going to be using is a AAA+ Unfoldase molecule. The data was originally collected here in Toronto by John Rubenstein in his lab, specifically Zev Ripstein, who was leading this project, and they published this a couple of years ago. As I mentioned yesterday, this was a really interesting data set because the team was able to take 170,000 raw particles without even actually doing any 2D classification in this case, throw them straight into a 5-class Ab-initio reconstruction and resolve both the inactive, well-known 6-fold symmetric state of the unfoldase, as well as the previously not seen before active state of the unfoldase unfolding one of its siblings in the ice. And that was a coincidental discovery that it just so happened because the sample concentration was so high that this happened. But it turns out with sample concentrations that are so high, there are some extra steps and advanced parameters that we need to use to be able to replicate this kind of result. So we're going to do that by starting with the same particle set that they used and trying to get to the same result. And that's going to involve a deep dive into 2D classification and ab-initio reconstruction, which are the next topics that we want to cover. So what I'm going to do is switch back to CryoSpark and show for the practical students and everyone else who's watching how we're going to do this. We're actually going to be using particles that are had been prepared at that time in rely on star file format along with MRC files for the actual particle stacks. And we're going to show how to import that into CryoSpark. And then we will be processing that data through different ways of doing 2D classification and then a multi-class ab-initio reconstruction. And we'll follow that up with separate refinements of the different conformational states. And this is similar to the protocol and the practice that was used in this case study that I just mentioned, except that in that case, after ab-initio reconstruction, we also used heterogeneous refinement to recover the conformational difference between the open and closed state of the ion channel, which are a little bit similar and more difficult. I mean, ab-initio reconstruction was able to separate them, but to get a really good classification at high resolution, we used heterogeneous refinement. Whereas in this case, the two conformations are so different that heterogeneous refinement on its own can't find them, but ab-initio reconstruction can. So that's kind of what we want to see here happening. So the instructions for what we're going to do are shown right here in this instructions pane. And this has already been sent by email to all the practical participants. So please follow along here. What we're going to do is start in our project in the Stanford Slack instances. We're going to go ahead and create a new workspace within our project, specifically for this data set. And we can name it the same name as the data set that we're working with. Inside of that workspace, we're going to go ahead and create an import particles job. Import particle stack. Now the import particle stack job has several parameters that allow us to import particle stacks in various formats. It's most commonly used to import star file particle formats. And it can import various things, including the actual raw data, CTF parameters, locations, alignment parameters, and so on. And those can be used within CryoSpark for further downstream processing. What we're going to do in this case, in order to import this particle data, is to start with finding the actual star file that corresponds to the metadata about the particle. So that includes the paths to each particle MRC file on disk, as well as the CTF parameters of every particle and so on. So if we go to the directory where we have our data /scratch/training/Slack workshop data, there we will see dataset number 3, AAA. And that's where we're going to go. Inside of that folder, there's a directory called particles. And there we find a whole lot of MRCS files. These are MRC stack files for particle stacks, commonly used in many programs, CryoSpark as well, and rely on. And if we go to the last page, we'll see that there's also a particles.star file. And that star file, if we were to read it, it actually contains one row per particle, showing us where the particle is on disk and the CTF parameters of that particle. And that's what we need really to get started here. Since we're going to be doing our own ab-initio reconstructions and everything, we don't need any initial volumes or any other alignment information about the particles. So by selecting this star file and clicking select, we've now filled in the particle meta path input. The import particles job in CryoSpark is somewhat smart in that if you just give it a metadata file, like a star file, it will try by itself to search around the file system nearby to that file and find the other data that it's referring to. So for example, the MRC files, the particle stacks, etc. So we don't actually need to tell CryoSpark where the particle data is. It'll try to figure that out from what the star file says about the locations and names of those particles. In addition, the star file already contains all the information that we want about the microscope parameters, accelerating voltage, spherical aberration, and so on. And so we don't need to override those, although if we did want to override them, that's possible. So we can go ahead and queue this import job. And the import job shows us that it's loaded 171,000 particles. And now we see for the first time what the particles look like. And you can tell what I meant by concentration. In every particle image, the actual proteins are packed so tightly together that there's almost no empty space between them. And in every box, there's usually 5 or 6 or 10 particles. This is actually the condition that led to the formation of the active state of the enzyme between blotting and freezing time. So that's a good thing. But for image processing, it makes our life a little bit difficult since there's so many particles in the box. And that can change a lot of the way that algorithms react to this data. And that's what we're going to try and sort of investigate in this practical portion. So now that that data has been imported, the next thing we're going to do is go ahead and create a 2D classification job. So we're essentially starting from the point where if we had been processing this data from scratch, we would have imported the movies, done the motion correction, CTF estimation, particle picking, extraction of the particles, and we would come to exactly this point. And this is where we would start a 2D classification run. So we can take the imported particles that we have and connect them to our 2D classification job. These instructions are all listed here on the left as well. And in this case, we're going to run this 2D classification just with the default parameters as if we didn't know anything about this data set. That's what we would normally do if we were processing this data for the first time. That's exactly what we would do. I'm going to actually switch over, rather than using resources on this instance, I'm going to switch over to my own instance where I've already run that 2D classification job. So the 2D classification job with default parameters is what we're seeing here. And all the practical students should run this job, and it'll, after about 8 or 10 minutes, it'll complete and give us the results that look like this. What I'm going to do is two things. First, I'm going to show everyone the other advanced parameters that we can use in 2D classification, what they mean, and how to think about them. And then I'll explain which ones I've used in the following 2D class jobs, which I also want the practical students to emulate so that we can actually get better results on this data set. Okay, when we look at all the parameters, including the advanced parameters for a 2D classification job, the one that I'm building right here, we can see that there's a particle pre-processing section, and those are parameters about the particle data, particle image data itself. These parameters control whether or not we want to apply a window on each particle image. If you remember from our import job, the particle images are square boxes and they have content throughout. But generally speaking, because we're going to be rotating the images and constructing a 3D structure, we don't really care what is in the corners of the image. And in fact, sometimes what's in the corners can be distracting or make processing more difficult. So by default, all CryoSpark jobs that deal with particles apply a window to the particles. And that's a soft window that zeroes out anything in the corners of the image. And the size of that window is defined by these parameters. There are two parameters, one being the inner radius of the window, which is it's defined as a ratio of the box size. So that's 85% of the box. That's where the window starts. And the window goes to 0 at 99% of the box. So basically, we're just smoothly zeroing out the corners of every image. In some cases, it can be useful to change these window parameters, but I don't think we've ever seen a case where that's actually been very important. So we can leave those window parameters the same. In the 2D classification itself, there are many parameters to choose from. There's some that are very important for doing advanced 2D classification that comes up every now and then. The most important thing, of course, is the number of classes, and that's not an advanced parameter. We saw already yesterday, even on the T20S example, that between 50 and 100 classes on the same 10,000 particles, we can resolve a very different population of views and other types of differences between the classes that we get. So in a case where we have conformational differences, or we suspect conformational differences, or we have an asymmetric particle that has many more different looking views, we really want to use a larger number of classes. And that kind of goes hand in hand with the size of the data set. If you have 100,000 particles, then 50 or 100 classes is probably as many as you can reliably get before the number of particles per class becomes so small that you can't really see details anymore. Whereas if you have 500,000, a million particles, you could easily get up to 200-300 classes in 2D classification and still resolve lots of different viewing directions and conformations and everything. So right now we're going to run this just with 50 classes to see what we get. Well, actually, that's what's happening already in the job that we started, but I'm going to continue going through the advanced parameters a little more. So the number of classes we'll leave as 50. The resolution two resolution values that we get to choose here. One is a maximum resolution that we are going to consider during 2D classification, and that sets the maximum resolution of the 2D classes that we can resolve. The default is 6 angstroms, which means that the 2D classes themselves are only being solved up to 6 angstroms. Any information in the images beyond 6 angstroms is not used during 2D classification, and therefore we don't expect the 2D classes themselves to have any details beyond 6 angstroms. So that's fine. By default, 6 angstroms is more than enough to get detail into our 2D classes where we can start to see secondary structure, helices, well, mostly lines as helices, and details like that. Just give me one moment. I'm going to try and reduce some of the background noise here. Sorry about that. Somebody is mowing their lawn. Quite loud. Okay, hopefully that's a little bit better. So where were we? Yes, the maximum resolution is the highest level of detail that we can hope to resolve in our 2D classification. We really aren't trying to get information beyond 6 angstroms. It's not helpful at this stage, but that's a parameter that you can play with. The other parameter is the maximum alignment resolution, and this is sometimes useful in cases where you're dealing with very poor quality data or extremely dirty data. Sometimes you don't want 2D classification to use higher resolution information to drive the alignments of images to the 2D classes. And that's because if you are starting to get noise buildup or other kinds of overfitting or aberrations in your 2D class images, it may be a result of the overfitting phenomenon that we described earlier. And a way to limit that overfitting is to stop 2D classification from looking at information beyond a certain resolution when doing alignments. That's different from the information that's captured in the 2D classes when we reconstruct the 2D classes from the images. But at the time of doing alignment, we may want to limit this to, let's say, 10 angstroms or something like that. Again, it's not commonly used, but sometimes for very difficult cases, it can be helpful. The next parameter is called the initial classification uncertainty factor. And this is something I'm going to come back to in detail when I talk about ab-initio reconstruction, since both 2D classification and ab-initio reconstruction have a similar parameter of this type. What this parameter controls is a little bit of extra information, guidance that we're giving the algorithm, the 2D classification algorithm, to tell it what kind of 2D class separation we want to achieve. It's a little bit difficult to explain, and for anybody who's actually trying to use it, I would highly recommend reading this tooltip text over and over until it starts to make sense. But essentially, a small value of this number will cause the 2D classification job to very quickly become certain about the assignment of particles to classes. And what that means is that at the beginning, the classes are randomly initialized, and there's no information about which particle belongs to which class. After a couple of rounds of classification and reconstruction, some classes, or most of the classes, will start to converge towards some common pattern that's in the data. And that might be a real particle, it might be junk, it might be something else that's commonly repeated. If this number is set small, let's say a value of 1, then we're indicating to the algorithm that we want it to settle down on the classification that it has right from the beginning. And that'll encourage the algorithm to separate particles from junk and other things that are very different. On the other hand, if we set this value large, let's say 10, what that tells the algorithm is that early on, it shouldn't trust the classification of particles at all. And so it should continue to evolve the 2D classes and the reconstructions that it's creating for a longer time and allow particles. If you recall yesterday, I mentioned that 2D classification in CryoSpark, or all classification in CryoSpark, is probabilistic. That means every particle can belong to multiple classes with some probability. What this factor will do is that if you set it at a large value, is that at the beginning, every particle will be allowed to belong to many classes. And that will shape all of the classes to look more similar to each other at the beginning, and then slowly diverge into multiple different views or conformations that are all more similar to each other. So that can be a helpful way if we want to focus the algorithm towards finding more classes that are spanning the diversity of views versus more classes that span the junk and all the other things in the sample. So for example, in a lot of cases, if you're doing 2D classification, if you do it with 50 classes, you might find that the last 10 or 20 classes are almost empty. They have just a few particles and they're mostly corresponding to junk. If you don't want to waste those 10 or 20 classes and you actually want to find 50 different viewing directions or conformations, then increasing this number can help to kind of force the algorithm to explore more similar classes. Hopefully what I'm explaining kind of makes some sense. When you try it out on some data, it'll become a little more clear what that intuitively means. We won't do that today though. The next parameters, and the ones that we're actually going to use today, are dealing with an idea of masking our 2D classes so that we only focus on the central part of every image. And that's exactly the problem in our crowded data set. In our crowded data set, if we look at the images, they have multiple particles. And if we look at our 2D classes with default parameters, what we actually got are lots of different distinct classes, but they are all describing different kinds of images, not in terms of the viewing angle or conformation of the protein, but the arrangement of multiple neighboring proteins. So there are, for example, pairs of proteins or triplets of proteins or 4 proteins beside each other, or pairs of a side view and a top view together. All of these arrangements, or 2 top views, all of these arrangements are all distinct, and each particle image fits into one of these classes, and that's exactly what 2D classification is supposed to do. But this doesn't help us because we weren't trying to separate the classes based on the arrangement of neighbors. We were trying to focus on the viewing angle and conformation of the protein itself. And that's exactly what the circular masking methods that we use are built to address. The first one, the parameters that are actually here are, first of all, to enable circular masking, which is enabled by default, but if you don't provide a circular mask diameter, then it's not used, just like in the first case. If you do provide a circular mask diameter, and for those who are following in the practical, what I'd like you to do is take your first 2D classification job, make a clone of it, and then in that job, leave all the other parameters the same, but set the circular mask diameter to 150 angstroms. That's also written here in step number 3 of our instructions, and then you can go ahead and run that job. What that does is it tells our algorithm that we don't want to solve any 2D classes that have any information or density outside of 150 angstroms away from the center. And that does exactly what we expect. All the classes now have a mask applied during optimization, not just at the end, but during optimization, so that they end up focusing on just what fits in a 150 angstrom circle. And that helps us to now resolve many different viewing directions of the particle. We can see we have lots of diversity of different side views, oblique tilted views, top views of different kinds. And we can start to see that there's something funny where we have this repeated motif of a side view of a particle with a little cloud of density. And that happens many times. That's actually the active state of the protein. And the cloud is the blurred out substrate, which is another unfoldase molecule that's being unraveled. And you can even see in this 2D class that the symmetry is slightly off. The circular symmetry that we expect in the inactive state when you're looking at a side view, that everything's the same around the circles, something's a little bit off in these classes. So we can already kind of tell that something's going on in our data, and we might end up finding out something interesting. So this is exactly the kind of result that we wanted from our 2D classification. And the big change that we had to do to get this was to apply that circular windowing. Like I said, by default, that's not engaged, but you can always provide a circular mask diameter. You can also provide an outer diameter if you want to change how soft the mask is, but by default, it's set to 20% larger than the inner diameter. There are also some options. Part of what this method of masking does is an operation that we call recentering, where during the optimization of the 2D classes, if, for example, I go back to the beginning of this 2D classification job, at the beginning, each class is a random blob, randomly shaped blob that fits inside of our window. As iterations move forward, the classes start to optimize themselves closer and closer to the actual particle that we're looking for. During this process, it's important that the actual particle remains inside of the window. If we don't enforce some kind of centering prior that tells the algorithm that we want the protein to be in the middle of the window, we'll get, instead of individual particles, we'll get half a particle on one side and half a particle on the other, and other kinds of weird configurations, just like we did the first time in this case. Like if you just applied the window to these results, many times you wouldn't have a particle in the middle, and that's a problem that we want to overcome. So for that, we have recentering, and by default, that's engaged. What recentering does is it takes the 2D classes at every iteration, picks up the regions that have the most density beyond a threshold of 20% of the maximum density, and finds the centroid of that density and moves that to the middle. So at each iteration, we're kind of bringing the density back to the center of the window, and that helps us to make sure that the classes remain centered and focus exactly on what we want. The next parameter I'm going to discuss is one that is commonly used, an advanced parameter. It's called force max over poses and shifts. And what this parameter controls, first I'll explain where it's useful. It's commonly used when you're dealing with difficult data sets of either very small proteins or proteins that are small, or like the ice is a lot thicker than the protein and the signal to noise ratio or contrast is poor. In both of those cases, the effect that we get is that there's less useful signal in every image for aligning particles together. And at those times, what we want is to, just like we're unsure about classification during 2D classification, we want to be probabilistic about assignment of orientations in 2D classification. This is also widely known as marginalization in the statistics and inference literature, and pretty much generally speaking for statistical optimization problems. Marginalization refers to the idea that rather than picking a single pose, because we don't actually know the pose of the structure of the protein that we want to align, we want to, instead of picking a single one, allow each protein molecule, each single particle image to remain uncertain about which poses it belongs to and use all of the different poses weighted by their probability, just like we do for classification. And so turning off this force max means force taking only the maximum likelihood pose instead of being, instead of marginalizing. If we turn this off, we will end up allowing every particle to remain in multiple poses that are simultaneously considered, and that helps for very low signal to noise data or very small particles. It's something that's definitely worth trying on any data. It just makes the algorithm take longer, maybe like 3 or 4 times longer for the same amount of data. Okay, we can also choose, I'm not going to cover some of the other options that are almost never used. We can add some extra iterations at the end if we want to continue to try and converge. We can also change, actually none of these parameters are widely used at all. Yeah, I won't talk about any of the other parameters since they're almost never used, but for 2D classification, finally, we can opt to parallelize the computations of alignment and reconstruction over multiple GPUs. In this case, the amount of communication between the GPUs is a little bit extra, or it's not perfectly parallelizable. And so the speed up you get from multiple GPUs isn't quite linear. 2 GPUs isn't twice as fast as 1 GPU. We're working to change that so that 2D classification and all the other reconstruction jobs in CryoSpark can be used on multiple GPUs with a nearly linear speed up. That'll be hopefully deployed in an upcoming version of CryoSpark, but so far, you probably, beyond 2 GPUs, the returns from adding more GPUs are probably diminishing. But if you're working with multi-million size particle data sets, which is often the case, using 2 or 4 GPUs here can help quite a bit. So I think those are all the advanced parameters that I wanted to talk about. And I think, yeah, we've already inspected the results of both types of 2D classification. So we know what we were looking for and how to tell that our 2D classes are actually good. The next thing that the practical participants should do is a select 2D job. So you can do that by going to the job builder and creating a select 2D job. Connecting the particles and class averages from your 2D classification with the windowing. This is step 4 now out of our steps here, and running that job. And in terms of selecting the classes, what we want to do is choose the classes that correspond to our particle and not anything else. In this case, after the windowing, the 2D classes are quite clean and there's lots of great classes. Everything in the first 3 rows is definitely something we want to keep, including these strange classes where we can see that cloud of extra density. And maybe up to this point, we want to keep everything so far. So all of those. In fact, these are all probably also good particles. We probably don't want the particles that are so off center in terms of their particle picking that they're always in pairs. So we'll leave that one aside. We can probably take this one. There are also some classes that look like a different object. Some kind of, these 3 classes that look like some kind of helical tube. I don't know, maybe some of the images had some sort of other thing present. Even in the original classification, you can see that there's this one class that has some other kind of object in the mix. And I don't think we want to include that. I'm not really sure what it is. So we'll skip that one, and we'll take everything else that looks like it could be our particle. And just get rid of anything that's obviously not similar to the particle that we're looking for. Okay, and click done. We should have somewhere around 90,000 or 100,000 particles left at the end of this. Oh, I have 140, sorry, that's a different data set. We should have around 150,000, 140 or 150,000 particles left at the end of this. And then what we're going to do after that select 2D job is to start an ab initio reconstruction with 3 classes. And that's what's going to help us resolve the heterogeneity in this data set and actually solve both the active and inactive states of the structure. So we can do that by, again, going to the job builder, selecting an ab initio job, ab initio reconstruction, and connecting the particles, only the selected particles from our select 2D job to the ab initio reconstruction. In ab initio reconstruction, we'll come back to talk about all the advanced parameters, but we can set the number of classes to 3. And that's going to create this ab initio reconstruction job, and then we can go ahead and run that. Okay, so once all the practical participants have gotten to that point, we'll later come back to do some more refinements of the different conformations that we find. But for now, I think we can head back to the slides, answer a few questions, and then I can continue talking about the advanced, some of the conceptual notions around heterogeneity, ab initio reconstruction, how many classes to choose, how to tell if they're good or not. And yeah, so any questions about anything that's come so far?
Yes, so we have a number of questions about 2D classification and advanced parameters. So first of all, in our example, we noticed that we had a lot of crowding and also smaller particles. So we use the windowing option, or rather applied a circular mask. How do we know what to set the diameter of the circular mask to, or what might be too narrow or too large?
Great question. There isn't an exact answer for that, but you will immediately see if you run a 2D classification, like I can just do that now, clone this job and run it with a different mask. Let's say I choose only 50 angstroms. What I'll see pretty much right away as soon as that job starts running is that my mask is clipping the edges of the particle, and what I'm getting in my 2D classes are just bits of my protein rather than the entire thing. Likewise, if the mask is too big, what we'll see is, again, the same phenomenon. Again, the same phenomenon that we saw without any masking, which is that instead of individual proteins, many of our 2D classes will contain pairs or triplets, and that's exactly what we want to avoid.
Perfect,
so here
thank you.
With only 50 angstrom diameter, there's no way that our protein is going to fit into this little circle.
Okay, so essentially, to some extent, trial and error and having an eye for what the size of the protein is.
Right. Although at this point, from particle picking and other things that came before, you probably do have an idea of the diameter of the particle. And you can also measure it based on the techniques we talked about yesterday.
Perfect. Some other parameters that we touched on were the max resolution and the max alignment resolution. If we have rather featureless particles, for example, proteins that are actually in a micelle, like membrane proteins, which of those parameters would we change, and what kinds of values might we be looking to apply?
So that's also a very good question. Definitely if you're working with a protein that is embedded in a micelle and the mass of the micelle is on the same order as the protein. So for example, a protein that's fully encased in the membrane. In that case, because of the micelle, which is disordered, the overall signal to noise ratio in terms of the actual protein that we want to align during 2D classification is very low. And so in that case, it's definitely worth to try this force max over poses option, turning that off to allow for marginalization over the poses. It's also a good idea if you start to see signs of overfitting, which in 2D classification generally look like streaks showing up in the background behind the protein or connected to the protein, anything like that, you probably want to choose a maximum alignment resolution to a slightly lower value, maybe 10. But if that's kind of a trade-off, because in many cases, if the protein is small or encased in the membrane, the only details about it that can be used to drive alignments appear at higher resolutions. For example, they may be the actual secondary structure that allows us, if the protein is, for example, symmetric and inside of a micelle, it looks kind of the same at low resolutions in all of these orientations. And it's only the small details that help us align it. So in that case, maybe you want to increase the maximum resolution that we're going to consider to 4 angstroms, so that you have a better chance of using the secondary structure information to align the particle. You can also, in those cases, extend the number of iterations that 2D classification will do, changing this number of online expectation maximization iterations to something like 40 or 50. You can also increase the number of particles that 2D classification looks at every iteration, other than the final iterations, by changing the batch size per class. You can make that, let's say, 200 or 500, and that will force 2D classification to consider more particles right from the beginning. And that can also help with smaller particles and those that have less signal.
Perfect. Conversely, what if we are actually doing a low resolution reconstruction for some reason? What should we set our maximum resolution to in that case?
Great. So for example, if you're working on a very large protein, you don't need a lot of high resolution detail to align a huge object. So you can set your maximum resolution to, let's say, 10 or 12. This actually has a huge benefit computationally, because in 2D classification, one of the first things we do, I'll just pick this one. One of the first things we do is to automatically determine the size in terms of box size or in terms of downsampling that we're going to use for the 2D classes themselves. Not the images, but the 2D classes. Since if we're only going up to 4 or 6 angstroms and our pixel size is 0.5 angstroms, we don't need to store the 2D classes in such a high resolution volume when they possibly, or such a high resolution image when they can't possibly contain details beyond 6 angstroms. And so the first thing we do is set the box size of the volume of the classes based on that initial resolution or maximum resolution that you set. So for very large images and very large particles, you can change this to 10, 12, even 20 if you don't think you need better than 20 angstrom 2D classes.
Thank you. We also discussed switching off force max over poses shifts for smaller particles. If we do that, should we also increase the number of 2D classes? Is there any relationship or any benefit from doing that?
Not a direct one. I mean, computationally, things get more and more expensive as you add more 2D classes, but from a conceptual or theoretic perspective, no. As you add more 2D classes, you're asking the algorithm to find more clusters and naturally subdivide the data further. So if you have few particles and they're low quality or very small particles, and you try to go for too many classes, you'll end up in a scenario where there just aren't enough images to spread amongst all those classes. And so each class ends up having not enough images to average into a higher resolution 2D class. And so you might get worse results in that case.
We also talked about recentering for this particular data set. In 2D classification, after we do recentering, do we then need to go back and actually re-extract the particles again?
We don't.
For down processing? Sorry.
We don't have to. I mean, it's a possibility. It's not something that we support as like a easy workflow in CryoSpark. It could be done manually, but it's definitely not necessary. The recentering doesn't actually change the particle data at all. And the fact that we're able to get very good 2D classes after recentering means that we were able to align by shifting the 2D classes against the particle images very well to get these good 2D classes. And so we already know that without recentering or re-extracting the particles, the current particles that we have can be well aligned in terms of shifts. So that's a good indicator. Re-extraction is really not, at least in our hands, not something that we commonly do. And generally speaking, I don't believe that it drives a huge benefit in any cases, except very rare, strange edge cases.
You touched a little bit on the batch size parameter as well. Can you please discuss how we would actually assign that or when we might use that parameter?
Sure. The batch size per class relates to how we do optimization in the 2D class scenario. So far, we've seen two different kinds of optimization methods used in cryo-EM reconstruction. One was the stochastic optimization that was used for ab initio reconstruction, and one is the iterative refinement or expectation maximization that's used for 3D reconstruction, 3D refinement. In 2D classification, we're actually using kind of a hybrid of those two. One way to do 2D classification would be to take your current estimate of the 2D classes and compare every 2D class to every particle image in the whole data set, and then use those assignments and angular alignments to recover new 2D class images. That's a very computationally expensive thing to do. And given that we're only looking for 2D classes up to, let's say, 6 angstroms, we really don't need to see the whole data set. So the batch size per class controls, at the early stages of this optimization, how many images we need to look at. Similar to an ab-initio reconstruction where we use small random subsets of the data, in this case, we do the same thing with larger subsets. And the batch size per class, if you take the number of classes, in this case 50, multiply by this number 5 to get 5,000, that's how many images we look at in the early stages of 2D classification. At a certain point, to get better 2D classes and alignments of all the particles, we do have to look at the entire data set a few times.
Thanks. And now once we've set and are satisfied with all the parameters in our 2D classification and we move on to actually selecting the 2D classes, can you please explain what are the different statistics that we see there? So specifically the number and ECA and the class averages?
For sure. So what I'll do is I'll just clone this select 2D job and run it again so I can show you that in action. Okay. So in this 2D classification job or select 2D job, we're able to see all of the actual template images as well as a few statistics that Sarah mentioned. There are obviously the number of particles. That's an easy one. That's just how many particles out of our total set of particles. At the top, you can see the total number of particles. How many of them fell into this class? How many of them are most likely to be appearing in this class? That is one of the parameters. Another one is the estimated resolution of the class. Now this one is a little bit, I mean, it's exactly what it says, an estimated resolution, but it's not something that you can trust in every way. You can trust it in the sense that it estimates the resolution to which this 2D class has been resolved. But it's not always the case that only those classes with a high resolution are worth keeping. The reason is that the resolution that you can resolve a 2D class depends heavily on the number of particles in the class. So classes with large numbers of particles often have high resolutions and are almost definitely things you want to keep. But in the mid-range, there may be a class with just a few number of particles, like these two classes that are side by side. If we zoom in a little here, you can see that this 9 angstrom class has about the same number of particles as this 12 angstrom class. And you can definitely see that in this case, we're seeing some details in there that in this case are not present. We just see lots of noise in this case. So it could be that these particles are for whatever reason aligning less well or are broken or somehow damaged. But this resolution value isn't necessarily a perfect separator of good and bad classes. In this case, for example, because this to my eye looks more or less like my protein of interest, I would be more interested in keeping it than throwing it away, even though the resolution estimate here is poor. On the other hand, you may have small classes that have few particles that just by the low number of particles like this one, low number of particles lead to a lower resolution. But again, in this data set context, I know that this is actually a good class that I want to keep. So just because the resolution is poor doesn't mean you should throw it away. If the resolution is very poor, then you probably do want to throw it away. But like this 15 angstrom class or this 17 angstrom big blob. But that's a decision that every user, unfortunately, right now has to make. The other statistic that we see, ECA, is a little bit tricky to explain. It is related to the notion that I mentioned that classes in CryoSpark classification is probabilistic. Every particle at the end of a 2D classification has a probability distribution over the classes. So it may be that one of the particles belongs 95% to one class, and the other 5% is spread out amongst a few other similar classes. That probability assignment is some sort of metric about the confidence in which we're able to classify particles and could be related to the quality of the class. So for example, if we have a class where all the particles in the class have a very high confidence that they belong to that class, and not to anything else, then maybe that's a sign that it's a good class. On the other hand, if we have a class where almost all the particles belong only 50% to that class and 50% to another class, that could mean it's not a very good class. Again, not always, but sometimes. So what this number means, it is the average across all the particles in this class of how many other classes do those particles have a significant probability of belonging to. So when this number is small, like 1, it means that all the particles in this class belong only to one class, which is this one. When it's big, like this one, 2.1, that says that on average, all the particles in this class belong to 2 classes with substantial probability. So that can mean 2 things. Either we have 2 classes that are very similar to each other, and so naturally every particle belongs 50% to both, or the particles are such that they have features that don't really match up with anything, and so they belong a little bit here, a little bit there. Again, that's not a perfect separator of good and bad classes, but something that you can look at. By and large, this decision of good and bad classes is done based on the number of particles and by eye, pretty much. There are some techniques that are in development for automatically determining good and bad classes, but they're not perfect yet.
Great. And the last question for this section is specific to this AAA plus Unfoldase dataset, sorry. And so specifically, how did you know that in some of those classes that you said, I'm going to keep this, I know it's a good class. How did you know that that little bit of fuzz that we see in the particular class average is actually relevant to you, or is some kind of interest, protein of interest, and not that the particle picking was just done wrongly or off center?
That's a great question. A priori, knowing nothing about the biological context, you don't know that. And if you were processing this data with a view of just getting a high resolution structure and not knowing anything about the biological context, you very well might throw away these particles that look like they're somehow deformed or wrong. And I'm conjecturing here, most likely the team that was originally processing this data was aware that they're dealing with an unfoldase. And so there's some notion that the unfoldase could unfold something and have some active state. So I think anybody who's working on a protein that's supposed to have some kind of mechanistic function would always be looking out for signs of something happening to it in terms of a conformational change. Secondly, in this case, I'm doing this all post hoc. Like, we already know what the refined structures are like. We already know that if we go back to our slides, that we expect the active state to look like this, where it has a symmetry broken version of the particle and this blurred out section. So we know what to look for already. In practice, the team that actually did this didn't do 2D classification. They decided that, all these particles look probably fine. Let's just throw them all into Ab-initio reconstruction and see what we get. So they actually didn't have to worry about this problem at all. They didn't have to select 2D classes. And that's an equally valid strategy that you can even try right off the bat. If your particle data is already sufficiently clean, and this is something we mentioned earlier as well, then Ab-initio reconstruction can actually be an even more powerful way to separate good and bad particles at the same time as separating conformations and figuring out 3D structures. So in this case, we know that you can take all the particles and just put them into a 5-way Ab-initio reconstruction and find both structures that we're looking for. And these will have most of the population of particles, and just a few of them will go into these junk classes and some of them into this double particle class. So that's kind of the answer to the question.
Awesome. And sorry, one last question just to follow that up. Since we know that we're expecting to see some classes that have this partially unfolded second molecule, does it make any sense to increase the circular mass in the 2D classes greater than 150 angstroms so that a larger portion of that fuzz or unfolded protein can actually be included in the class? Does that make sense?
Absolutely. And this is a great example of the kind of investigative data processing that you really have to do in real life if you're working on an interesting sample like this, where that's exactly the kind of thing that you can only test by trying it. And if it's easy to try, as it would be in CryoSpark, you can just go ahead and do that, even probably simultaneously while you're doing it with 150 angstrom window. You can try with 200 or 250 and just see what you get. In real life, that is exactly how you would figure things out. So yeah, I would say that's a good idea. In this case, I happen to know, or we can kind of infer that the second molecule in the unfolding case is very floppy. Like it's just attached to the first one by the end of its whichever terminus that's being unfolded. And so it's totally flexible, just attached by a tether. And so we don't really expect that we would be able to see much more of it or kind of solve any structure of it, since it's not even likely to be facing the same way or anything relative to the first molecule, at least as far as we can tell. So I wouldn't bank on that, but it's definitely worth trying.
Great. We
I
have
have-
just,
I had
sorry,
a
go
couple
ahead.
questions about that, and it seemed like those classes, as you made them, as you made that window big enough to include the neighbors, the center of gravity uh, of what you chose as quote the middle of the thing moved to actually kind of in between the well-defined protein blob and the
Right.
thing to which it was attached. Was that kind of an automatically done thing, or
Yes, I see what you mean. Like in this case, right?
yeah, they're shifted a little bit. Yeah.
Exactly. Yeah, that is exactly what the recentering method does, is that literally what it does is it takes the 2D class average before recentering. It thresholds it at 20% of its maximum density, and any density that's above 20% is used in computing the center of mass. So if this fuzzy area is above 20% of the maximum density, which it looks like it is, then it would be counted in the centering and therefore be used to move the center of mass around and the center position. And so that's why we would get this kind of skew offset of the center of the actual protein,
One
which is not
thing,
a bad thing, because in 3D reconstruction, all of the proteins have to be aligned to the same reference. And so even if in the different viewing directions of this active state, the protein is a little bit centered or not centered in the box, all the particle images will be aligned to that in different views.
one just another thing from my uh, curiosity is that
Yeah.
the fuzzy blob, if it was perched on top of a top view, do you know how many views actually ended up with the fuzzy blob perched on top when you're looking at that to see whether it had any kind of whether you got enough views of that top view
Right.
to see?
That's a great question. So I'm going to answer that by actually looking at the orientation distributions of my proteins. So the first class here in this ab initio reconstruction that's already complete, the first class, again, we're looking at 3 central slices. The orientation distribution looks a little funny. And the reason for that is that ab initio reconstruction, first of all, doesn't have any notion of up or down or sideways. The protein itself can be oriented in an arbitrary position or angle, rotation angle, inside of the box. And so it's not necessary that azimuth and elevation correspond to like around the ring and up and down in this case because of ab initio reconstruction. So right now what we're looking at, this protein is actually sideways in the box. And so a front view, what we would normally consider a front view, is actually a top view. And what we would ordinarily consider like a great circle going between the equators are side views. And so that's what this orientation distribution looks like. This is a front view, AKA top view. This is a bottom view. And this band is the equatorial band around the ring.
And
So
it
we
goes
see in
around the North
this
Pole and South Pole. Yeah.
it crosses the North and South Pole. So we can see that in this case, we're getting a great distribution of views because we have exactly what we want. Lots of side views and enough top and bottom views and a pretty wide band of slightly different tilts and so on. So that's great. This is the other case. This is the active state of the enzyme. And here you can, in this one slice, you can see the fuzz of the second particle. Here now, again, the particles are oriented in a different random position. And we can again see that here, this band is the equatorial band that goes around the ring. So we're getting lots of side views. But compared to before, there's far fewer top and bottom views in a relative sense. Before, there were lots of top views about equal in terms of particles per angular spacing between top and side views. But now there's far, far more side views than top views. So we know that our active state does have a different orientation distribution than our active state. So I don't have the exact numbers to quantify, but from this you could quantify exactly how many top views of the unfolding molecule there are in the mix, at least as far as we can classify them.
Yeah, thanks.
No problem. It's also worth noting that this junk class from the 3 class ab initio, first of all, in terms of the number of particles, you can see them on the right here. Class 0, the fully intact symmetric class, has about 100,000 particles. The active state has about 40,000 particles, and this junk class has about 7,000 or 8,000 particles. And that junk class, in terms of its viewing distribution directions, has only a band of side views, nothing really on top and bottom. And the structure of it is some weird hybrid of two molecules together. So it's not something that we really want to trust or say that like this is really a structure that's there, because this viewing direction distribution doesn't really give enough information to believe in this 3D structure. So we would just categorize all these as junk particles and go forward with two confirmations that we can solidly trust here. And in fact, that's what we want to do next. All of the practical participants should look at your ab-initio reconstruction, figure out which class is which in terms of confirmations. Again, because it's ab-initio, there's no guarantee that class 1 will be the biggest or class 2 will be the smallest or anything like that, and they're not sorted. So then you can see which class is which, and you can go ahead and create a homogeneous refinement new job. If you take the particles from the inactive state and the volume from the inactive state, that one you can refine with all default parameters, except the symmetry we can set to C6, since we do believe that to be what we expect to find. I'll go ahead and run that. And then you can do the same thing, this time with the other class, that's the active state. Create a homogeneous refinement new job. Connect the particles from class 1 and the volumes from class 1, and this time leave it in C1 symmetry. And we can go ahead and run that as well. And that's going to refine for us when we come back in a few minutes the two conformational states of this protein.
Great. I think that's a perfect time to head off for the lunch break.
Okay,
so
actually,
sorry, go ahead.
there is one thing. If we can spare 5 minutes, I just want to start off the jobs for the next practical, since they take a little time, maybe 30, 40 minutes. So I'd like to start those off for the practical participants. It should only take about 5 minutes or so. So for practical participants, if you can, continue watching my screen, we're going to go down to this Apoferritin example, which is what we're going to work on next. So if you can create in your project a new workspace and call it Apoferritin, I always spelled this wrong. In there, we're going to create an import job, this time of a different kind. This time we're importing CryoSpark results from a different CryoSpark instance. And so we're going to use the import result group job. And that can be used generically to import any kind of CryoSpark output into a different project. So we're going to be importing, and you only need to provide one file path for importing CryoSpark results. That's a .csg file, CryoSpark group file. And we'll find that if you go into, and this needs a little bit of attention, each user, if you recall your project number, if you go into your /scratch/training/projects directory and find your own project, mine is P6, so I'm going to go into there. Inside of your own project, you should see another folder called Slack Workshop Data. It's a symlink to the actual Workshop Data folder. It has to be inside of the project directory, since in CryoSpark you can only import things that have been already moved inside of your project directory to keep the project directory self-contained. So we can go to that symlink and find our number 6 dataset, Apoferritin, go into the particles folder and choose the CSG file. Those instructions are all written here on this page as well, and in the instructions that were sent out. You can go ahead and select that and then run that job, and that will bring in the particle images and other things that we need for this Apoferritin dataset. Next, we need to import a 3D volume, which we're going to use as an initial model for our refinements. And there we can use the import 3D volumes job. Again, the instructions are all here on the side. In the import 3D volumes job, we're just going to choose a path. It's also inside of this 6 Apoferritin dataset or directory, and it's called map.mrc. So we can go ahead and select that and also run that import job, everything else being default. Finally, we can go and start a couple of refinement jobs. So we're going to choose one homogeneous refinement, new. To it, we're going to connect the particles that we just imported and the volume that we just imported. And we're going to change a few parameters. We're going to set the symmetry to octahedral, that's O, capital O. We're going to turn off the do symmetry alignment parameter. I'll be explaining all of these later when we come back from lunch. And we're going to set the initial low pass resolution to 15 angstroms instead of 30. And finally, if you scroll down a little bit, we're going to turn on the option called minimize over per particle scale. And then we're going to queue this job. I'm not actually going to do it on this instance. Once you've queued that job, you can select the job card and clone it. That'll make another copy of the refinement job with the same inputs and other parameters already set. And now we're just going to turn on 2 more parameters. These are advanced parameters, so make sure the toggle is on. One parameter called optimize per particle defocus, and one parameter called optimize per group CTF parameters. And then we'll queue that and run that as well. So again, all of those instructions are here and they've been sent to the practical participants already. For those who are watching, what we're trying to do here is just set up 2 refinements of the same particles, one without CTF refinement and one with CTF refinement. That's something, an advanced topic that we're going to be talking about just when we return from lunch and the other sessions that we have. Okay, so that's all I wanted to show. And if there's any other urgent questions or anything we should take care of right now, otherwise we can head for lunch and come back in an hour.
Oh, I think we're okay for now for questions.
Great.
Okay, we will meet back again at 1:10 Pacific time, and I'll put that up on the screen. Okay.
Great.